Close your eyes and imagine this. You are floating in the most profound darkness imaginable. Not the darkness of a moonless night or a windowless room. This is the darkness that existed before light itself was born. Before matter. Before time. Before space. This is where our story begins, in the singularity that preceded everything. 13.8 billion years ago, the universe was compressed into a point smaller than an atom. All the mass, all the energy, all the potential for every star, every galaxy, every planet, and every living thing that would ever exist was crushed into an infinitesimally small point. The temperature was beyond incomprehensible, beyond any scale we use today. And then, in an instant that defies human imagination, it exploded. But here's what most people get wrong about the Big Bang. It wasn't an explosion in space. It was an explosion of space itself. Space and time burst into existence simultaneously. There was no before, because time itself began at that moment. Think about that for a second. Time, the very thing by which we measure all existence, had a beginning. Every second that has ever ticked, every moment you've ever experienced, every yesterday and every tomorrow, all of it traces back to that singular event. In the first fraction of a second, something extraordinary happened. The universe underwent a period of inflation, expanding faster than the speed of light. Now you might be thinking, wait, nothing can travel faster than light. And you'd be right. Nothing can travel through space faster than light. But space itself? Space can expand at any rate it wants. In less time than it takes for light to cross the nucleus of an atom, the universe grew from smaller than a proton to larger than a galaxy. As the universe expanded, it cooled. And as it cooled, the fundamental forces that govern everything began to separate. First, gravity split off. Then the strong nuclear force, which holds the nuclei of atoms together. Then the electromagnetic force and the weak nuclear force differentiated. These four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, these are the puppet masters of reality. Every single thing that has ever happened in the universe, from the formation of black holes to the firing of neurons in your brain right now, is the result of these four forces. For the first 380,000 years, the universe was opaque. It was so hot and dense that light couldn't travel. Photons, the particles of light, would get absorbed and re-emitted constantly, unable to move freely. The universe was like a thick fog. But as it continued to expand and cool, something magical happened. The temperature dropped enough for electrons to combine with protons and form the first atoms, mostly hydrogen with a bit of helium. This moment is called recombination, and it changed everything. When recombination happened, light was suddenly free to travel. The universe became transparent. Those photons that were released during recombination have been traveling through space ever since, and we can still detect them today. We call it the cosmic microwave background radiation. It's the afterglow of creation, the oldest light in the universe, and it's everywhere. Right now, as you listen to these words, you are bathed in the faint whisper of the Big Bang itself. The early universe was remarkably smooth, but not perfectly smooth. There were tiny variations in density, slight ripples in the fabric of space and time. And these tiny imperfections would become the seeds of everything we see today. Gravity, that most familiar yet most mysterious of forces, began to pull matter together at these slightly denser regions. Over millions of years, clouds of hydrogen and helium gas began to collapse under their own gravity. These clouds grew denser and hotter. And when the temperature and pressure at their cores became high enough, something spectacular occurred. Hydrogen atoms began to fuse together, forming helium and releasing tremendous amounts of energy. The first stars ignited. These first stars were nothing like our sun. They were monsters, hundreds of times more massive, burning with a fierce blue-white light. They were the cosmic furnaces that would forge the elements necessary for life. You see, in the beginning, the universe had only hydrogen, helium, and trace amounts of lithium. That's it. No carbon. No oxygen. No iron. All the elements that make up your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, none of that existed yet. These massive first stars lived fast and died young. In just a few million years, they exhausted their fuel. And when they died spectacularly, as supernovae. These explosions were so powerful that they created temperatures and pressures high enough to forge all the heavier elements: carbon, nitrogen, oxygen, silicon, iron, gold, uranium. Every element heavier than helium in your body was created in the nuclear furnace of a dying star or in the violent explosion that followed. Carl Sagan famously said we are made of star stuff. But it's even more specific than that. The atoms in your left hand might have come from a different star than the atoms in your right hand. You are a collection of nuclear waste from stars that died billions of years ago, scattered across space and reassembled into the form listening to these words right now. As generations of stars lived and died, the universe became enriched with heavy elements. Clouds of gas and dust, now containing these elements, collapsed to form new generations of stars. And around these stars, something new began to happen. The leftover material, the dust and gas that didn't fall into the star, began to clump together, forming planetary disks. Think about this process. Tiny grains of dust, floating in the vacuum of space, occasionally colliding and sticking together. Over millions of years, these grains became pebbles. Pebbles became boulders. Boulders became mountains. Mountains became planetesimals, objects kilometers across. And planetesimals, through countless collisions, became planets. Our own solar system formed this way, 4.5 billion years ago. In a cloud of gas and dust in an unremarkable region of an unremarkable spiral galaxy, gravity pulled matter together. The sun ignited at the center, and around it, the planets began to form. The inner planets, Mercury, Venus, Earth, and Mars, formed from rock and metal. The outer planets, Jupiter, Saturn, Uranus, and Neptune, grew massive enough to capture and hold on to thick atmospheres of hydrogen and helium. Early Earth was a hellish place. Barely formed, still glowing with the heat of its creation, bombarded constantly by asteroids and comets. The young planet's surface was molten rock. There were no oceans, no atmosphere as we know it, no life. Just endless volcanic activity and impacts from space. Then, about 4.5 billion years ago, something dramatic happened. A Mars-sized object, which we call Theia, crashed into the young Earth. The collision was so violent that it melted both bodies. Debris was thrown into orbit around Earth, and from this debris, our moon coalesced. This impact had profound consequences. It tilted Earth's axis, giving us seasons. The moon stabilized that tilt, preventing wild variations in climate. And the moon's gravity created tides, which may have been crucial for the emergence of life. As Earth cooled, water vapor in the atmosphere condensed and fell as rain. It rained for millions of years, forming the first oceans. Where did all this water come from? Some was released from volcanic activity, water that had been trapped in the rocks when Earth formed. But much of it was delivered by comets and water-rich asteroids that continued to bombard the planet. The same cosmic bombardment that made Earth a hellscape also brought the water that would make life possible. Somewhere, somehow, in those early oceans, chemistry became biology. We don't know exactly how it happened. This is one of the great mysteries that remains. But about 3.5 billion years ago, the first living cells appeared. They were simple, just membranes surrounding self-replicating molecules. But they could do something extraordinary. They could make copies of themselves. Life, at its core, is chemistry that can reproduce. And once you have reproduction, you have variation. Once you have variation, you have natural selection. Once you have natural selection, you have evolution. And evolution, given enough time, can produce wonders that seem impossible. For the first 2 billion years of life on Earth, nothing much seemed to happen. Single-celled organisms, bacteria and archaea, dominated the planet. But these simple cells were performing a quiet revolution. Some of them, the cyanobacteria, evolved the ability to capture energy from sunlight and use it to convert carbon dioxide and water into sugar and oxygen. Photosynthesis. This was perhaps the most important biochemical innovation in Earth's history. These photosynthetic bacteria began to pump oxygen into the atmosphere. At first, the oxygen reacted with iron dissolved in the oceans, forming rust that settled to the ocean floor. We can still see evidence of this today in banded iron formations, layers of red rock that mark the transition. But eventually, all the dissolved iron was used up, and oxygen began to accumulate in the atmosphere. This was a catastrophe for most life on Earth at the time. Oxygen was toxic to the anaerobic organisms that had dominated the planet. It was the first great extinction, caused not by an asteroid or a volcano, but by life itself. Yet this catastrophe created opportunity. Oxygen is highly reactive, and organisms that could harness its reactivity could extract far more energy from food than was possible before. Aerobic respiration evolved, and life became turbocharged. About 2 billion years ago, something remarkable happened. One bacterial cell was engulfed by another, but instead of being digested, it survived inside its host. This was the origin of mitochondria, the powerhouses of the cell. This partnership, this endosymbiosis, gave rise to complex cells with specialized internal structures. These eukaryotic cells would become the ancestors of all plants, animals, and fungi. For the next 1.5 billion years, single-celled eukaryotes diversified and experimented with different ways of living. Then, around 600 million years ago, something changed. Cells began to stick together, to cooperate, to specialize. Multicellular life had arrived. The Cambrian explosion, 540 million years ago, was when life truly went wild. In a geological blink of an eye, most of the major animal body plans we see today appeared in the fossil record. Eyes evolved. Shells and skeletons evolved. Predation became sophisticated. The arms race between hunters and hunted drove an explosion of diversity and complexity. Life moved on to land about 470 million years ago. First plants, then arthropods, then vertebrates. Each wave of colonization transformed the planet. Plants covered the continents in green, creating soil, releasing oxygen, changing the climate. Insects evolved flight, the first animals to conquer the air. And about 370 million years ago, our ancestors, lobe-finned fish, dragged themselves out of the water and began to breathe air. The history of life on Earth has not been smooth. 5 times, mass extinctions have wiped out the majority of species on the planet. The worst, the Permian-Triassic extinction 252 million years ago, killed 96% of all marine species and 70% of land vertebrates. The causes varied: massive volcanic eruptions, asteroid impacts, climate change, ocean acidification. But life persisted. Life always finds a way. The most famous extinction, the one that killed the dinosaurs 66 million years ago, was caused by an asteroid 6 miles wide slamming into what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons. It created an earthquake that shook the entire planet, triggered tsunamis that dwarfed anything in human history, and threw so much debris into the atmosphere that it blocked out the sun for years. 3/4 of all species went extinct. But in the ashes of that catastrophe, mammals, which had been small and insignificant for the 150 million years that dinosaurs ruled, suddenly had room to evolve. They diversified rapidly, filling the ecological niches left vacant. And among those mammals, about 6 million years ago, a lineage of African primates began to walk upright. Our ancestors, the hominins, evolved in Africa. They walked on 2 legs, freeing their hands to carry things, to make tools, to gesture and communicate. Their brains grew larger. They learned to control fire, to cook food, to work together in complex social groups. And about 300,000 years ago, Homo sapiens, anatomically modern humans, appeared. For most of our history, we were just another species struggling to survive on the African savanna. But about 70,000 years ago, something changed in our brains. We developed what some call behavioral modernity, the ability to think symbolically, to plan for the future, to create art and music and mythology. We began to tell stories. And those stories allowed us to cooperate in ways no other species could. We spread out of Africa and across the world. We reached Australia 45,000 years ago, Europe 40,000 years ago, and the Americas at least 15,000 years ago. Everywhere we went, we adapted, inventing new tools, new techniques, new ways of life suited to each environment. We learned to farm, to domesticate animals, to build cities and civilizations. The scale of human impact on Earth has accelerated dramatically in recent centuries. In the blink of an eye, geologically speaking, we've gone from small bands of hunter-gatherers to a global civilization of 8 billion people. We've split the atom, mapped our own genome, sent robots to Mars, and detected gravitational waves from colliding black holes billions of light years away. We've developed technologies that would seem like magic to our ancestors just a few generations ago. But let's zoom back out, because Earth and humanity are just a tiny part of a much larger cosmic story. Our planet orbits an average star in the suburbs of a spiral galaxy we call the Milky Way. The Milky Way contains somewhere between 100 and 400 billion stars. Think about that number. If you counted one star per second, it would take more than 10,000 years to count them all. And each of those stars is a sun, potentially with its own family of planets. The Milky Way is not alone. It's part of a small group of galaxies we call the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies. And the Local Group is part of the Virgo supercluster, which contains thousands of galaxies. And the Virgo supercluster is just one of millions of superclusters in the observable universe. How many galaxies are there in the observable universe? Current estimates suggest around 2 trillion. 2 trillion galaxies, each containing hundreds of billions of stars. The number of stars in the universe exceeds the number of grains of sand on all the beaches on Earth. And we now know that most stars have planets. The universe is teeming with worlds. Some of these worlds must harbor life. The chemistry of life, carbon-based chemistry in liquid water, seems almost inevitable given the right conditions. We've found organic molecules, the building blocks of life, in meteorites, in comets, in the clouds of gas between stars. The ingredients for life are everywhere. And planets with liquid water, planets in the habitable zone around their stars, appear to be common. We don't know yet if we're alone. We've searched for signals from other civilizations, listened for radio transmissions, looked for signs of mega-engineering projects. So far, silence. This is the Fermi paradox. If intelligent life is common, where is everybody? Maybe we're the first. Maybe civilizations inevitably destroy themselves. Maybe they're out there but communicating in ways we haven't thought to look for. Or maybe they're simply too far away, separated by distances so vast that communication is impractical. The universe is big. Really big. The observable universe, the part we can see, has a radius of about 46 billion light-years. That's the distance light has been able to travel in the 13.8 billion years since the Big Bang, accounting for the expansion of space. But the universe beyond what we can see is almost certainly much, much larger. It might even be infinite. And here's something that should keep you awake at night, or given the nature of this documentary, help you sleep with a sense of cosmic perspective. We can only see 4.9% of the universe. That's all the normal matter, all the atoms, all the stars and gas and dust and planets. The other 95.1% is dark. 27% is dark matter, matter that doesn't emit or absorb light but whose gravity we can detect. 68% is dark energy, a mysterious force causing the expansion of the universe to accelerate. Dark matter holds galaxies together. Without it, galaxies would fly apart. We can map dark matter by observing how it bends light from distant galaxies through gravitational lensing. We know it's there, we can see its effects, but we have no idea what it's made of. It doesn't interact with normal matter except through gravity. It passes through you right now, billions of dark matter particles every second, and you never notice. Dark energy is even more mysterious. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as everyone expected, but speeding up. Something is pushing space apart, overcoming the attractive force of gravity. We call it dark energy, but that's just a label for our ignorance. We don't know what it is or why it exists. The fate of the universe depends on dark energy. If it remains constant, the universe will continue to expand forever, faster and faster. Galaxies outside our local group will eventually recede so quickly that their light can never reach us. The sky will grow dark. Stars will eventually burn out. Black holes will evaporate through Hawking radiation. In a googol years, 10 to the power of 100 years, the universe will be cold, dark, and empty. This is the heat death of the universe. But there are other possibilities. If dark energy weakens over time, expansion could slow and gravity could eventually win, pulling everything back together in a big crunch, the mirror image of the Big Bang. Or if dark energy strengthens, we get the Big Rip, where the universe expands so violently that eventually even atoms are torn apart. We don't know which fate awaits us. We're still in the infancy of understanding the cosmos. Let's talk about black holes, because nothing captures the imagination quite like a region of space where gravity is so strong that not even light can escape. Black holes form when massive stars run out of fuel and collapse. If the star is massive enough, nothing can stop the collapse. The core is crushed to infinite density, creating a singularity, surrounded by an event horizon, the point of no return. Anything that crosses the event horizon is gone forever, at least from the perspective of the outside universe. Time itself behaves strangely near a black hole. If you watch someone fall into a black hole, you would see them slow down as they approach the event horizon, their image becoming redder and dimmer, frozen at the edge for eternity. But from their perspective, they would cross the horizon in finite time, though they wouldn't survive the experience. The tidal forces, the difference in gravitational pull between their head and feet, would stretch them into a long, thin strand in a process lovingly called spaghettification. At the center of most galaxies, including our own Milky Way, lurks a supermassive black hole. The one at the center of our galaxy, Sagittarius A-, has a mass of about 4 million suns. We've watched stars orbit around it, moving at incredible speeds, their orbits tracing out the gravitational influence of this invisible monster. In 2019, we even captured an image of a supermassive black hole, not ours, but the one at the center of the galaxy M87, 65 million light-years away. It has a mass of 6.5 billion suns. The image showed the shadow of the black hole surrounded by a glowing ring of superheated matter spiraling into oblivion. Black holes are not cosmic vacuum cleaners. Despite popular misconception, they don't suck things in any more than any other object with the same mass. If the sun were replaced by a black hole of equal mass, Earth's orbit wouldn't change. We'd freeze to death without sunlight, but we wouldn't spiral into the black hole. You have to get very close to a black hole, crossing the event horizon, before there's no escape. Stephen Hawking showed that black holes aren't entirely black. Quantum effects at the event horizon cause black holes to emit radiation, now called Hawking radiation. Through this process, black holes slowly evaporate, losing mass over time. A solar mass black hole would take 10 to the 67 years to evaporate, far longer than the current age of the universe. But eventually even black holes die. Let's travel outward from our galaxy to explore the large-scale structure of the universe. Galaxies are not randomly scattered through space. They're organized into groups, clusters, and superclusters, connected by filaments of galaxies separated by vast cosmic voids. This cosmic web is the largest known structure in the universe. It formed from those tiny density fluctuations in the early universe, enhanced by the gravity of dark matter. In the voids, space is relatively empty. But along the filaments and at the nodes where filaments intersect, galaxies cluster together. The Coma cluster contains over 1,000 galaxies. The gravitational pull of such clusters is so strong that it can bend light from galaxies behind them, creating multiple distorted images of the same galaxy. This gravitational lensing has become a powerful tool for studying both distant galaxies and the distribution of dark matter. Galaxy collisions are common in these dense environments. When galaxies collide, the stars themselves rarely hit each other. Space is mostly empty after all, but the gas clouds collide, triggering bursts of new star formation. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they'll merge, creating a new elliptical galaxy that astronomers have already nicknamed Milkomeda. Don't worry, the chances of our solar system being disturbed are minimal. The Sun and Earth will likely survive the merger intact. But the Sun won't last forever. Our star is about halfway through its main sequence lifetime. In about 5 billion years, it will exhaust the hydrogen in its core. The core will contract and heat up, while the outer layers will expand. The Sun will become a red giant, swelling to perhaps 100 times its current size, engulfing Mercury and Venus, possibly reaching Earth's orbit. Earth's oceans will boil away. The atmosphere will be stripped off. Life as we know it will be impossible. Eventually, the Sun will shed its outer layers, creating a beautiful planetary nebula, a glowing shell of gas expanding into space. All that will remain is the hot, dense core, a white dwarf about the size of Earth but with about half the Sun's mass. A teaspoon of white dwarf material would weigh tons. With no fuel left to burn, the white dwarf will simply cool over trillions of years, eventually becoming a cold, dark black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. More massive stars meet more dramatic ends. When they exhaust their fuel, their cores collapse, and they explode as supernovae. For a few weeks, a single supernova can outshine an entire galaxy. The explosion disperses all the elements forged in the star's core across space, enriching the interstellar medium with the raw materials for new stars, new planets, and potentially new life. Every atom heavier than helium in your body was created in such a stellar furnace and dispersed by such an explosion. You are literally made of dead stars. The most massive stars become black holes when they die, but stars of intermediate mass become neutron stars. A neutron star is the densest form of matter we know of aside from black holes. A typical neutron star is only about 20 kilometers across but contains more mass than the Sun. A teaspoon of neutron star material would weigh 1 billion tons. The gravity is so strong that it crushes electrons and protons together to form neutrons. The entire star is essentially one giant atomic nucleus. Some neutron stars spin rapidly and emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If one of these beams points toward Earth, we detect regular pulses of radiation. We call these objects pulsars. Some pulsars spin hundreds of times per second, as fast as a kitchen blender. They're the most accurate clocks in the universe, more accurate than any atomic clock we've built. When two neutron stars orbit each other, they emit gravitational waves, ripples in spacetime itself predicted by Einstein's general theory of relativity. These waves carry energy away from the system, causing the orbit to decay. Eventually, the neutron stars spiral into each other and merge in a cataclysmic explosion called a kilonova. This event produces intense gravitational waves, a gamma-ray burst, and creates heavy elements like gold and platinum. The gold in your jewelry was forged in such a collision billions of years ago. In 2015, we detected gravitational waves for the first time, from two merging black holes over 1 billion light-years away. This opened a completely new way of observing the universe. We're no longer limited to electromagnetic radiation, light in all its forms. We can now listen to the universe through gravitational waves. We've detected dozens of events so far: black hole mergers, neutron star mergers, each one teaching us something new about the universe. The universe is full of violent events. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang. They release in a few seconds more energy than the Sun will emit in its entire 10 billion year lifetime. We think they're caused by the collapse of very massive stars or by neutron star mergers. Most of their energy is focused into narrow jets. If one of these jets pointed at Earth from a nearby galaxy, it could strip away our ozone layer and cause a mass extinction. Fortunately, they're rare and usually very far away. Quasars, the brilliant cores of distant galaxies powered by supermassive black holes consuming matter, are the brightest objects in the universe. A quasar can outshine an entire galaxy of stars. They were more common in the early universe when galaxies were forming and black holes were actively feeding. The most distant quasars we've observed are so far away that we see them as they were when the universe was less than 1 billion years old. Their light has been traveling to us for over 90% of the universe's history. The expansion of the universe means that the most distant objects we can see are moving away from us faster than the speed of light. This doesn't violate relativity because they're not moving through space faster than light. Space itself is expanding between us. This expansion stretches the wavelength of light, shifting it toward the red end of the spectrum. We call this cosmological redshift. The most distant galaxies are so redshifted that their visible light has been stretched into infrared wavelengths. The James Webb Space Telescope, launched in 2021, is designed to see these distant, redshifted galaxies. It's already revolutionizing our understanding of the early universe, finding galaxies that formed just a few 100 million years after the Big Bang. These galaxies are older, more massive, and more organized than our theories predicted. The universe apparently got started making galaxies earlier and more efficiently than we thought. But Webb is finding more than just distant galaxies. It's analyzing the atmospheres of exoplanets, planets orbiting other stars. By watching how starlight filters through a planet's atmosphere as it passes in front of its star, we can determine what gases are present. We've found water vapor, carbon dioxide, methane, even possible signs of complex organic chemistry. We're on the verge of being able to detect biosignatures, chemical signs of life, in the atmospheres of distant worlds. Imagine the moment when we detect oxygen and methane together in an exoplanet's atmosphere, a combination that on Earth is maintained by life. Or when we detect industrial pollutants, unambiguous signs of technology. The confirmation that we're not alone would be the most profound discovery in human history. It would tell us that life is not a cosmic fluke but a natural consequence of cosmic evolution. And if life is common, then intelligence might be common too. But what is intelligence? We tend to define it anthropocentrically, in terms of what humans do. But intelligence might take forms we don't recognize. The octopus, for instance, has a distributed intelligence, with neurons throughout its body and arms, not centralized in a brain like ours. Its experience of consciousness, if it has one, must be radically different from ours. And that's just on Earth. On worlds with different environments, different evolutionary histories, intelligence might be utterly alien. Consider this scenario. We receive a signal from space, clearly artificial, clearly a message. But when we decode it, we can't understand it. Not because we lack the technology, but because the concepts it contains are so foreign to our experience that we can't even grasp what kind of information it is. Like trying to explain color to someone born blind, or music to someone born deaf, there may be modes of thought and perception that are simply inaccessible to beings with our evolutionary history. Or perhaps intelligence inevitably converges on certain solutions. Mathematics, for instance, is the same everywhere in the universe. An alien civilization would discover the same laws of physics, the same mathematical theorems. 2 + 2 = 4 on every planet orbiting every star. Perhaps intelligent beings, despite evolving independently, would have more in common than we think. The search for extraterrestrial intelligence, SETI, has been ongoing for over 60 years. We've searched thousands of star systems, listening for radio signals, looking for laser pulses, even searching for signs of massive engineering projects like Dyson spheres, hypothetical structures that would encompass a star to capture all its energy. So far, nothing. The universe seems stubbornly silent. There are many possible explanations. Maybe life is common but intelligence is rare. Maybe intelligence is common but technological civilizations are short-lived, destroying themselves or losing interest in broadcasting. Maybe they're out there but using communication methods we haven't thought to look for, like neutrinos or gravitational waves. Or maybe they're deliberately staying quiet, wary of revealing their presence to potentially hostile civilizations. There's another possibility that's both hopeful and humbling. Maybe we're early. The universe is only 13.8 billion years old. Stars will continue forming for trillions of years. Most of the stars that will ever exist haven't been born yet. Most of the planets that will ever exist haven't formed yet. Maybe we're among the first intelligent civilizations to arise. Maybe the universe is waiting for us and others like us to fill it with life and thought and wonder. But we're getting ahead of ourselves. Before we colonize the galaxy, we need to become a truly spacefaring civilization. Right now, we're confined to Earth, with a handful of people occasionally visiting the International Space Station. We've sent robots to every planet in our solar system and visited the Moon briefly 50 years ago. But that's it. We're still in the cradle. Becoming a multi-planet species won't be easy. Mars is the obvious next step. It has a day length similar to Earth's, about 24.5 hours. It has ice at its poles and likely underground. Its atmosphere, though thin and mostly carbon dioxide, provides some protection from radiation. And it's relatively close, only about 6 months away with current technology. But Mars is harsh. The average temperature is -80 degrees Fahrenheit. The atmospheric pressure is less than 1% of Earth's. You can't breathe the air. The soil is toxic with perchlorates. There's no magnetic field, so the surface is bathed in radiation from the sun and cosmic rays. Any colony would need to be largely underground or heavily shielded. Water and oxygen would need to be extracted from the soil and ice. Food would need to be grown in greenhouses. It would be like living in Antarctica, but worse, much worse. Yet Mars has resources. It has water, carbon dioxide, nitrogen, minerals. With enough energy and technology, it could support a self-sustaining colony. Solar panels could provide power, though dust storms occasionally block the sun for weeks. Nuclear reactors would be more reliable. Settlers could extract rocket fuel from the atmosphere, using the Sabatier reaction to combine carbon dioxide and hydrogen into methane and water. This would enable travel back to Earth or to other destinations in the solar system without needing to bring all the fuel from Earth. The outer solar system holds wonders too. Jupiter's moon Europa has a global ocean beneath its icy crust, kept liquid by tidal heating from Jupiter's gravity. That ocean might harbor life, simple single-celled organisms living in the warm water near hydrothermal vents on the ocean floor, similar to life around deep-sea vents on Earth. We're planning missions to drill through Europa's ice and explore that ocean. What we find could rewrite our understanding of life's potential in the universe. Saturn's moon Titan is the only moon with a thick atmosphere. It has lakes and rivers and rain, though they're made of liquid methane and ethane, not water. The surface temperature is -290 degrees Fahrenheit, far too cold for water-based life. But some scientists speculate that Titan could host a completely different kind of life, one based on liquid methane instead of water, using different chemistry. It's an alien world where we might find truly alien biology. Saturn's moon Enceladus, like Europa, has a subsurface ocean. Geysers at its south poles shoot water vapor and organic compounds into space, material from that hidden ocean. We've flown through these plumes and detected complex organic molecules. Enceladus might be one of the best places in the solar system to look for life beyond Earth. But even if we establish thriving colonies on Mars, Europa, Titan, and elsewhere in our solar system, we're still trapped around one star. To become a truly space-faring civilization, we need to travel to other stars. And that's a problem. The nearest star, Proxima Centauri, is 4.2 light-years away. With current spacecraft, it would take about 70,000 years to get there. We need faster spacecraft. Nuclear propulsion could reduce the travel time to centuries. Fusion rockets could get us there in decades. Antimatter rockets could do it in years. But these are all technologies we don't yet have. And even at a significant fraction of the speed of light, interstellar travel is a multi-generational endeavor. The people who arrive won't be the people who left. Generation ships, massive spacecraft designed to support a population for centuries or millennia, are one solution. The ship would be a self-contained world, with agriculture, industry, schools, hospitals, everything a society needs. Children would be born, live, and die aboard the ship, their lives dedicated to a mission they didn't choose, to deliver their distant descendants to a new world. Or we could use cryogenic sleep, freezing colonists for the journey and reviving them upon arrival. We don't have this technology yet, but it's not impossible. Suspended animation would allow a single generation to make the journey, waking up centuries later in a new star system. Though there would be psychological challenges. Everyone and everything you knew would be dead. You'd be alone in the universe except for your fellow colonists. There are wilder ideas too. Light sails pushed by powerful lasers could accelerate tiny probes to a fraction of the speed of light, reaching nearby stars in decades. Wormholes, if they exist and can be stabilized, could provide shortcuts through space, allowing near-instantaneous travel across vast distances. And some physicists speculate about warp drives, distorting space-time itself to move faster than light without technically moving faster than light. These ideas are at the edge of theoretical physics. And we don't know if they're actually possible. But the fact that they don't violate known physics means we can't rule them out. If we do reach other star systems and find habitable planets, should we colonize them? If they're lifeless, the answer seems obvious. But what if they already harbor life, even simple microbial life? Do we have the right to displace or contaminate an entire biosphere? These are ethical questions we'll need to answer. And there's the Fermi paradox again. If space travel is possible, if intelligence is common, then where are the aliens? The galaxy is about 13 billion years old. Even traveling at a small fraction of the speed of light, a civilization could colonize the entire galaxy in a few million years. That's a blink of an eye on cosmic timescales. So why hasn't someone already done it? Why isn't the galaxy teeming with civilizations? Maybe advanced civilizations realize that physical expansion isn't necessary or desirable. Maybe they turn inward, creating virtual realities far richer than anything the physical universe can offer. Why travel for decades or centuries to a new star when you can create entire universes in a computer? Maybe the universe seems empty because everyone is off in their own simulated paradises. Or maybe the universe is teeming with life and intelligence, but they're staying hidden, watching to see what we do. Maybe there's a galactic ethics, a prime directive that says you don't interfere with developing civilizations. Maybe we're being observed, studied, catalogued, and we won't be contacted until we reach some threshold of maturity. Or maybe, and this is the dark possibility, civilizations inevitably destroy themselves. Maybe the same intelligence that creates technology also creates weapons of mass destruction, environmental catastrophe, artificial intelligences that don't share our values. Maybe the universe is silent because every civilization that reaches a certain level of technology faces a great filter, a challenge so difficult that most fail. Maybe we haven't heard from anyone else because there's no one else to hear from. But let's be optimistic. Let's imagine that we navigate the challenges ahead, that we become a sustainable, mature, multi-planet civilization. What then? What is the long-term future of humanity and intelligence in the universe? On timescales of billions of years, the universe will look very different. Stars will continue to form from the remaining gas in galaxies, but gradually, the gas will be used up. Star formation will slow and eventually stop. The universe will grow darker as stars burn out and are not replaced. In about 100 trillion years, the last stars will die. The stelliferous era, the age of stars, will end. What happens then? For a long time, the universe will be dominated by stellar remnants, white dwarfs, neutron stars, and black holes, along with the planets and other debris orbiting them. These remnants will slowly cool, approaching the background temperature of space. The universe will be cold, dark, and quiet. But there will still be energy gradients, temperature differences that can be exploited. An advanced civilization could potentially survive by clustering around black holes, using the Hawking radiation they emit as an energy source. Black holes also distort time, so time would pass more slowly near the event horizon. A civilization there could stretch its subjective existence far into the deep future. Eventually, even black holes will evaporate. A solar mass black hole takes 10 to the 67 years to evaporate. A supermassive black hole could last 10 to the 100 years. But eventually, they're gone. And then what? In some versions of physics, protons themselves decay, with a half-life of perhaps 10 to the 34 years. If that's true, then eventually even matter as we know it will cease to exist. The universe will be nothing but a thin soup of photons, electrons, positrons, and neutrinos, growing ever more dilute as space expands. This is the heat death of the universe, the state of maximum entropy. No structure remains. No energy flows. Nothing happens. It's the end of everything. Not in a dramatic collapse, but in a slow fade to eternal darkness and cold. But maybe that's not the end. Some theories suggest that quantum fluctuations could eventually produce new Big Bangs, new universes bubbling up out of the void. Each universe would have its own laws of physics, its own constants, its own history. We might live in a multiverse, an infinite ensemble of universes with every possible configuration. In some of these universes, the laws of physics don't allow for atoms or stars or life. In others, they allow for structures far more complex than anything we can imagine. We happen to find ourselves in a universe where the laws of physics permit our existence. This is the anthropic principle. We observe the kind of universe we do because if it were different, we wouldn't be here to observe it. But let's return to the present, to our universe, to our time. We live in a remarkable era. The universe is old enough to have produced structures like galaxies and stars and planets, but young enough that stars still shine, that life can exist, that minds can contemplate the cosmos. We find ourselves on a small planet orbiting an average star in an ordinary galaxy in a vast universe that seems indifferent to our existence. Yet here we are, collections of atoms and molecules that have organized themselves into forms that can think, feel, wonder, and dream. We are the universe becoming aware of itself. Every human who has ever lived, every thought, every emotion, every work of art, every scientific discovery, every moment of joy and suffering, all of it has happened on this pale blue dot suspended in a sunbeam. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. But that shouldn't make us despair. It should fill us with purpose. We are the custodians of Earth, the only home we've ever known. We're the guardians of a biological heritage 3.5 billion years in the making. We're the bearers of consciousness, that mysterious property that allows the universe to know itself. Think about the journey we've described. From the Big Bang to the present day, from the first subatomic particles to galaxies, from lifeless chemicals to living cells, from single cells to complex organisms, from simple animals to beings capable of understanding their own origins. This is an epic story, a cosmic narrative of which we are a part. And the story isn't over. It's still being written. What comes next depends on us. We can choose to use our intelligence and technology to create a future of abundance, exploration, and wonder. Or we can squander our potential, allowing short-term thinking and tribal conflicts to destroy what we've built. The universe doesn't care which path we choose. The stars will continue to shine, galaxies will continue to collide, black holes will continue to devour matter, all completely indifferent to the fate of one species on one planet. But we should care. Because if we fail, consciousness might wink out in this corner of the universe. The experiment that is human civilization, this brief candle in the cosmic dark, might end. But if we succeed, if we navigate the challenges ahead, the possibilities are limitless. We could spread throughout the solar system, then to nearby stars, eventually throughout the galaxy. We could encounter other forms of life, other intelligences. We could unlock the deepest secrets of physics, master the manipulation of matter and energy at the quantum level, perhaps even learn to shape space-time itself. We could survive not just for centuries but for billions of years, adapting and evolving, becoming something beyond what we currently are. We might merge with our technology, transcending biology entirely. We might engineer new forms of life, create artificial intelligences that far exceed our own capabilities. The future could be stranger and more wonderful than anything we can imagine. Or we might remain essentially human, preserving our biology, our emotions, our way of experiencing the world, but extending our lifespans, eliminating disease and suffering, spreading throughout the cosmos while still retaining our humanity. There's no law of nature that says we must transcend our biology. We can choose to remain human if we wish. But whether we remain biological or become post-biological, Whether we stay in our solar system or spread throughout the galaxy, the greatest adventure lies ahead. We're at the beginning of our story, not the end. The universe is 13.8 billion years old, but it has trillions of years ahead of it. The age of stars, when the cosmos is alive with light and energy and possibility, is far from over. We live at a special time. We're among the first generations to understand the cosmos, to know our place in space and time, to detect gravitational waves and image black holes and sequence genomes. We're also among the last generations who will remember what it was like when humanity was confined to a single planet. The choices we make now, in this century, will echo across the eons. So as you drift off to sleep, contemplating the vastness and complexity of the universe, remember this. You are not separate from the cosmos. You are a part of it. The atoms in your body were forged in stars. The oxygen you breathe was created by ancient cyanobacteria. The consciousness you experience emerged from billions of years of evolution. You are intimately connected to the grand cosmic story. And that story continues. Every day, we learn something new about the universe. We discover new exoplanets, new galaxies, new phenomena that challenge our understanding. We push the boundaries of knowledge, driven by curiosity, by the desire to know, to understand, to explore. This is what makes us human. This is what makes us special. Not that we're the center of the universe, we're not. Not that we're particularly important on a cosmic scale, we're not. But that we can think, we can question, we can discover. We can look up at the night sky and wonder. And from that wonder comes science, art, philosophy, all the things that make life meaningful. The universe is vast and ancient and indifferent. But it's also beautiful and mysterious and full of wonders beyond imagining. And we get to be a part of it. We get to experience it, to explore it, to try to understand it. What an incredible privilege that is. So rest now, knowing that you are made of star stuff, that you are a way for the cosmos to know itself, that you are part of something much larger and older and grander than any individual life. Rest knowing that above you, even during the day when you can't see them, the stars are shining, galaxies are spinning, and the universe continues its grand cosmic dance. And perhaps, somewhere out there, on a planet orbiting a distant star, another being is looking up at their sky, contemplating the same questions, feeling the same sense of wonder. Perhaps they too are wondering if they're alone. Perhaps they too are just beginning their journey into the cosmos. We don't know if we'll ever meet them. We don't know what the future holds. But we do know this. The story of the universe is also our story. And it's a story worth telling, worth living, worth preserving for generations to come. Sleep well, fellow traveler. Dream of stars and galaxies, of worlds yet undiscovered, of futures yet unwritten. Dream of the cosmic ocean in which we all swim, vast and mysterious and beautiful beyond words. And when you wake, remember that you are part of something extraordinary. You are alive in a universe that permits life. You are conscious in a cosmos that, through you, becomes conscious of itself. That is the miracle. Not that the universe exists, though that too is remarkable. But that within the universe, matter can organize itself into forms that can perceive and think and feel and wonder. From chaos comes order. From simplicity comes complexity. From lifeless chemistry comes biology. From biology comes consciousness. From consciousness comes understanding. This is the story of everything. This is your story. This is our story. And the next chapter is waiting to be written. The universe began in fire, in unimaginable heat and energy. It will likely end in ice, in cold and darkness and entropy. But in between, in this brief cosmic moment when stars shine and planets orbit and life flourishes, there is light. There is warmth. There is wonder. We are lucky to be here, to witness this moment in cosmic history. We are lucky to be alive, to be conscious, to be able to contemplate our origins and our destiny. We stand on the shoulders of giants, of all the humans who came before us, who built civilization, who developed science, who asked questions and sought answers. And we have responsibilities to those who will come after us. To leave them a world worth inheriting. To leave them knowledge worth preserving. to leave them a future worth living. The cosmos is patient. It has waited billions of years for someone to notice it, to understand it, to appreciate its beauty. And now it has us. Flawed, finite, but filled with curiosity and wonder. We may be small, but our ideas can be vast. We may be mortal, but our impact can last for ages. We may be alone in the universe, or we may be one of many. But either way, we matter. We matter because we can create meaning in a universe that has none inherent in it. We matter because we can care, we can love, we can strive for something better. The stars don't know we exist. The galaxies don't care about our dreams. But we exist anyway. We dream anyway. We reach for the stars anyway. And maybe that's enough. Maybe that's everything. So close your eyes. Let the cosmic story wash over you. Feel yourself floating in the void, surrounded by the light of ancient stars, part of the great cosmic tapestry that connects everything to everything else. You are stardust pondering stars. You are the universe, experiencing itself. You are part of the story, and the story goes on. Rest now, cosmic traveler. The universe will still be here when you wake. Vast, ancient, mysterious, beautiful, and utterly, completely, magnificently real. Sleep well. The stars above us tell stories written in light that began its journey before humans existed. Photons that left distant suns when dinosaurs walked the earth are only now arriving at our telescopes. We are time travelers, looking backward with every glance at the night sky. The deeper we look into space, the further back in time we see. The most distant objects visible to our telescopes show us the universe as it was over 13 billion years ago, when it was young and wild and still forming its first structures. Consider what this means. When you observe a galaxy 10 billion light-years away, you're seeing it as it existed 10 billion years ago. That galaxy, if it still exists, looks completely different now. It may have merged with other galaxies. Its stars may have burned out and been replaced by new generations. But we'll never see what it looks like today because that light won't reach us for another 10 billion years. By then, humanity will either have spread across the cosmos or vanished entirely from the universe. This is the strange nature of cosmic observation. We can never see the universe as it is, only as it was. We live in a bubble of causality, able to observe only what light has had time to reach us. Beyond the observable universe lies more universe, perhaps infinite, but we can never see it. The expansion of space means that light from the most distant regions will never reach us. There are galaxies out there whose light is rushing toward us but losing the race against the expansion of space, destined never to arrive. The cosmic microwave background, that afterglow of creation we mentioned earlier, represents a kind of ultimate horizon. We can see back to 380,000 years after the Big Bang, but no further. Before recombination, the universe was opaque to light. We cannot observe directly what happened in those first moments. We must infer it from physics, from particle accelerators that recreate tiny portions of those extreme conditions, from mathematical models and simulations. But there are other ways to peer into the early universe. Gravitational waves travel through the opaque early universe unimpeded. A sufficiently sensitive gravitational wave detector could, in principle, detect signals from the first moments after the Big Bang. From cosmic inflation itself. We could observe creation directly, not through the medium of light but through the vibrations of spacetime itself. Neutrinos, ghostly particles that barely interact with matter, also pass through the opaque early universe. The universe is filled with a background of neutrinos from the Big Bang, analogous to the cosmic microwave background but from even earlier times. These cosmic neutrino background particles haven't been detected yet. They're incredibly difficult to detect because they interact so weakly with matter. But they're there, streaming through you right now, trillions every second, messengers from the first second of creation. The universe has layers of history that we're only beginning to read. Each new way of observing, each new wavelength of light, each new type of signal, reveals something previously hidden. When we first observed the sky in radio waves, we discovered pulsars and quasars and the cosmic microwave background. When we observed in X-rays, We found neutron stars and black hole accretion disks and the hot gas between galaxies. When we observed in gamma rays, we found the most violent explosions in the universe. Gravitational wave astronomy is in its infancy, barely a decade old. We've detected a few dozen events, mostly merging black holes and neutron stars. But imagine what we'll discover as our detectors improve. We might detect gravitational waves from the early universe, from cosmic strings if they exist, from the Big Bang itself. We might find completely unexpected sources, phenomena we haven't even theorized about yet. This has happened throughout the history of astronomy. Every time we've developed a new way of looking at the universe, we've been surprised. Nature is more creative than we are. The universe contains phenomena stranger than we imagined. Quasars, pulsars, gamma-ray bursts, gravitational waves, dark matter, dark energy, all of these were discovered, not predicted. Well, gravitational waves were predicted, but their detection revealed sources we hadn't anticipated. What else is out there, waiting to be discovered? What phenomena exist that we haven't detected because we haven't thought to look in the right way? The universe has already surprised us repeatedly. There's every reason to believe it will continue to do so. Consider the humble photon, the quantum of light. Every photon has a story. The photons hitting your eye right now from your lamp were created in the atoms of the lamp's filament just nanoseconds ago. The photons that warm your face from sunlight were created in the core of the sun over 100,000 years ago, though they were created as high-energy gamma rays. They scattered countless times, working their way out through the dense solar interior, gradually losing energy, until they emerged from the surface as visible light 8 minutes before hitting your face. Photons from distant stars have been traveling for years, centuries, millennia, or billions of years. They've crossed vast gulfs of emptiness, perhaps passing through clouds of gas and dust, perhaps being bent by the gravity of intervening galaxies, but maintaining their journey until they happen to strike your eye or a telescope mirror. And then, in an instant, their journey ends. They're absorbed, their energy transferred, and they cease to exist as individual photons. A multi-billion-year journey ending in an eye blink. But what a journey! That photon carried information across the cosmos. Information about the star that emitted it, encoded in its wavelength and polarization. Information about everything it passed through, imprinted as absorption lines in its spectrum. Every photon is a messenger, and by collecting billions of them, we reconstruct the stories of distant objects, of galaxies and quasars and supernovae, things we'll never visit but can study intimately through the light they emit. This is the power of astronomy. We can't perform experiments on stars. We can't manipulate galaxies. But we can observe, and from those observations, deduce the laws governing cosmic phenomena. We've learned that the same physics that works on Earth works everywhere. The spectral lines of hydrogen are the same in a galaxy 10 billion light-years away as in a laboratory. The constant of gravitation is the same throughout the observable universe. The laws of physics appear to be universal. Or are they? Some theories suggest that physical constants might vary in different regions of space or different epochs of time. The fine structure constant, which governs electromagnetic interactions, might have been slightly different in the early universe. The cosmological constant, related to dark energy, might change over time. These are subtle effects, difficult to detect, but if confirmed, they would revolutionize our understanding of physics. We think of the laws of nature as immutable, but they might be more like local bylaws, varying from place to place in a larger multiverse. Our universe might be just one bubble in an infinite foam of universes, each with different physical constants, different laws of physics, different numbers of dimensions. We happen to find ourselves in one where the constants are just right for stars and planets, and life to exist. This raises profound questions about the nature of physical law. Are the laws of physics necessary truths, the only way a universe could be? Or are they contingent, just one possibility among many? If the latter, why these laws and not others? Is there some deeper principle that determines which laws apply in which universe? These questions push at the boundaries of science and philosophy. They may be unanswerable, at least with our current methods. We can only observe our universe, not other hypothetical universes. But the questions are worth asking because they remind us how much we don't know, how many mysteries remain. Let's consider the nature of time itself. We experience time as flowing, as moving from past through present into future. But physics doesn't support this intuition. In the equations of physics, time is just another dimension, similar to space. The past, present, and future all exist equally. The flow of time is an illusion created by consciousness, by the way our brains process information and form memories. This view, called the block universe, suggests that all moments in time exist simultaneously. The universe is a four-dimensional structure, with 3 spatial dimensions and 1 time dimension, and everything that has ever happened or will ever happen exists within this structure. Your birth and your death, the formation of Earth and the heat-death of the universe, all exist as different locations in space-time, equally real, equally present. If this is true, then the future already exists. It's already out there, in the block universe, waiting for us to arrive. But this seems to eliminate free will. If the future already exists, then it's fixed, determined. Our choices are illusions. We think we're making decisions, but we're just following a script that's already been written in the fabric of space-time. Or perhaps the block universe is wrong. Perhaps the present moment is special, the only thing that exists. The past has ceased to exist, surviving only in records and memories. The future doesn't exist yet, it's genuinely open, undetermined. This view preserves free will and matches our intuition, but it's harder to reconcile with physics. These questions about time connect to questions about consciousness. What is consciousness? How does subjective experience arise from objective physical processes? Why is there something it's like to be you, experiencing this moment, rather than just unconscious information processing? This is the hard problem of consciousness, and nobody knows the answer. We can map brain activity. We can identify which neurons fire when you see the color red or feel pain or remember your childhood. But we can't explain why these physical processes are accompanied by subjective experience. Why isn't the brain just a biological computer, processing information without any inner experience? Some philosophers argue that consciousness is fundamental, a basic feature of the universe like mass or charge. Perhaps all matter has some rudimentary form of consciousness, and complex consciousness like ours emerges when matter organizes itself in sufficiently complex ways. This view, called panpsychism, is controversial. But it's taken seriously by some neuroscientists and philosophers. Others argue that consciousness is an emergent property, something that arises from complex information processing but isn't present in the individual components. Just as wetness emerges from water molecules but individual molecules aren't wet, consciousness emerges from neurons but individual neurons aren't conscious. This doesn't fully explain the hard problem, but it suggests a direction for investigation. There's also the possibility that consciousness plays a more fundamental role in the universe than we realize. Some interpretations of quantum mechanics suggest that consciousness is necessary to collapse the wave function, to turn quantum possibilities into classical actualities. This is highly controversial, and most physicists reject it, but it's an idea that won't quite die. Quantum mechanics itself is deeply strange. At the quantum level, particles don't have definite properties until they're measured. An electron isn't definitely in one place or another, it's in a superposition, simultaneously in multiple places. Only when you observe it does it choose a definite location. This is not just ignorance, not just us not knowing where the electron is. The electron genuinely doesn't have a definite position until it's measured. Einstein hated this. He famously said that God does not play dice with the universe. But quantum mechanics has been tested extensively, and it works. The universe really is fundamentally probabilistic. Outcomes aren't determined, they're only probable. There's genuine randomness built into the fabric of reality. This has strange consequences. Quantum entanglement means that two particles can be connected in such a way that measuring one instantaneously affects the other, even if they're on opposite sides of the universe. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments have confirmed that entanglement is real. The universe really is non-local in this weird quantum way. Some interpretations of quantum mechanics suggest that every time a quantum measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, the electron goes left, in another, it goes right. Both outcomes happen, but in different universes. This is the many worlds interpretation, and it suggests that there are countless parallel universes, one for every possible outcome of every quantum event. If many worlds is correct, then there are versions of you in other universes where you made different choices. There's a universe where you chose a different career, a different partner, a different life. There are universes where Earth's history went differently, where the dinosaurs didn't go extinct, where humans never evolved. There are universes where the constants of physics are slightly different and stars never formed. This is mind-bending stuff, and we don't know if it's true. Many worlds is one interpretation among several, and they all make the same experimental predictions. We may never be able to test which interpretation is correct. But the fact that serious physicists take these ideas seriously tells you how strange the quantum world really is. Let's return to the large-scale structure of the universe. We mentioned the cosmic web, the filaments and voids that organize galaxies. This structure emerged from tiny fluctuations in the early universe, amplified by gravity and dark matter over billions of years. Computer simulations can reproduce this structure remarkably well, starting from the initial conditions we observe in the cosmic microwave background and evolving forward using the laws of physics. These simulations require enormous computing power. They track billions of particles representing dark matter, gas, and stars, calculating gravitational forces and other physics over billions of years of cosmic time. The results match observations remarkably well, giving us confidence that we understand the basic processes governing cosmic structure formation. But there are discrepancies. Simulations predict more small galaxies orbiting the Milky Way than we observe. They predict that galaxies should have more dark matter in their centers than we observe. These are called the missing satellites problem and the core cusp problem. They might indicate problems with our understanding of dark matter, or they might be solved by including more detailed physics in the simulations. Dark matter remains one of the great mysteries. We know it's there from its gravitational effects, but we don't know what it's made of. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that don't interact electromagnetically but do interact through gravity and the weak nuclear force. Enormous experiments deep underground are searching for WIMPs, trying to catch one colliding with ordinary matter. So far, nothing. Axions are another candidate, much lighter than WIMPs but much more numerous. They were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force, but they could also be dark matter. Experiments are searching for them too. Or maybe dark matter is something completely unexpected, something we haven't thought of yet. Maybe it's primordial black holes, formed in the early universe. Maybe it's a modification of gravity rather than new particles. Maybe it's something even stranger. Dark energy is even more mysterious than dark matter. We discovered it in the late 1990s by observing distant supernovae. Type I supernovae have a known brightness, so by measuring how bright they appear, we can determine their distance. And by measuring their redshift, we can determine how fast they're moving away from us. The results were shocking. Distant supernovae were dimmer than expected, meaning they were further away than expected, meaning the universe's expansion has been accelerating. This shouldn't happen. Gravity should be slowing the expansion, not speeding it up. Something is pushing galaxies apart, overcoming gravity. We call it dark energy, but that's just a name for our ignorance. We don't know what it is. The simplest explanation is that dark energy is the cosmological constant, a term Einstein added to his equations and later called his biggest blunder. The cosmological constant represents the energy of empty space itself. Even vacuum has energy, according to quantum field theory. This vacuum energy has negative pressure, which in general relativity acts as a repulsive force, pushing space apart. The problem is that when we calculate how much vacuum energy there should be based on quantum field theory, we get an answer that's 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics. Either our calculation is wrong in some fundamental way, or there's some unknown mechanism that cancels most of the vacuum energy, leaving just the tiny amount we observe. This is the cosmological constant problem, and solving it might require a revolution in physics as profound as quantum mechanics or relativity. We might need to understand quantum gravity, the union of quantum mechanics and general relativity, something we don't yet have a complete theory of. String theory is one attempt at quantum gravity. It proposes that fundamental particles aren't point-like but are tiny vibrating strings. Different vibration modes correspond to different particles. Strings naturally include gravity, unlike other quantum theories. But string theory requires extra dimensions beyond the three of space and one of time we experience. These extra dimensions are supposedly curled up so small we can't detect them. String theory is elegant mathematically, but it hasn't made testable predictions yet. Some critics argue it's not even science, just mathematics. Defenders argue we need to be patient, that the theory is still developing and will eventually make predictions. The debate continues. Loop quantum gravity is another approach, proposing that space and time are discrete at the smallest scales, made of tiny loops rather than being continuous. This approach is mathematically rigorous but hasn't made many contact with experimental physics yet either. We need quantum gravity to understand black hole singularities and the Big Bang singularity. General relativity predicts that these are points of infinite density, where the laws of physics break down. But infinity usually means our theory is incomplete. Quantum gravity might eliminate these infinities, replacing singularities with something less extreme. What lies at the center of a black hole? We can't see past the event horizon, so we may never know observationally. But theoretically, general relativity predicts a singularity, a point where all the matter that fell into the black hole is crushed to infinite density. This seems physically impossible. Quantum effects should become important at tiny scales, potentially preventing true infinities from forming. Some theories suggest the singularity is replaced by a bounce, where the collapsing matter reaches a maximum density and then rebounds, possibly creating a new universe on the other side. Black holes might be doorways to other universes, though we could never travel through them and return to tell the tale. Stephen Hawking's work on black hole thermodynamics revealed deep connections between gravity, quantum mechanics, and thermodynamics. Black holes have temperature and entropy. They can evaporate through Hawking radiation. And there's a paradox. If a black hole evaporates completely, what happens to the information about all the matter that fell in? Quantum mechanics says information can't be destroyed, but if the black hole evaporates, where did the information go? This is the black hole information paradox, and it's been debated for decades. Hawking initially thought information was destroyed, violating quantum mechanics. Later, he changed his mind, arguing that information must somehow be preserved, perhaps encoded in the Hawking radiation in subtle ways. The paradox has driven developments in theoretical physics, leading to ideas like holography and the ADS/CFT correspondence. Holography suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. The entire universe might be a holographic projection from information encoded on a distant boundary. This sounds like science fiction, but it's taken seriously by physicists because mathematical evidence supports it in certain theoretical models. These ideas connect to questions about the nature of reality itself. Is the universe fundamentally made of matter and energy, or is it fundamentally made of information? Some physicists argue that information is more fundamental, that matter and energy are just ways information organizes itself. The universe might be, at its deepest level, a computational process, a cosmic algorithm running on some substrate we don't yet understand. This brings us to simulation theory, the idea that our reality might be a computer simulation created by a more advanced civilization. If we eventually develop the technology to create highly realistic simulations, and if those simulations can contain conscious beings, then there could be far more simulated minds than real ones. Statistically, you'd be more likely to be in a simulation than in base reality. This argument, made famous by philosopher Nick Bostrom, is controversial. It depends on assumptions that might not hold. Maybe it's impossible to simulate consciousness. Maybe advanced civilizations have no interest in creating such simulations. Maybe we're special in being in base reality. Or maybe the argument is sound, and we're in a simulation. If we are in a simulation, would there be any way to tell? Might there be glitches, bugs in the code? Could we find evidence of the computational substrate underlying reality? Some physicists have speculated about ways to test this, looking for anomalies in cosmic rays or limits on computational resources manifesting as limits on precision in physical measurements. So far, no evidence. But even if we are in a simulation, it doesn't change much practically. Our experiences are real to us. Our relationships matter. Our choices have consequences within the simulation. The simulation is our reality, whether it's base reality or not. These philosophical questions are fun to contemplate but difficult to resolve empirically. Science works best when we can test ideas through observation and experiment. Some questions might be beyond the reach of science, at least with current methods. But let's return to what we can observe and test. Let's talk about the formation of structure in the universe, from the largest scales down to the smallest. On the largest scales, we have the cosmic web. On smaller scales, galaxy clusters and individual galaxies. Within galaxies, we have stars, planets, asteroids, comets. And within planets, we have molecules, atoms, and subatomic particles. At each scale, different physical processes dominate. On cosmic scales, gravity and dark energy govern the evolution of structure. Within galaxy clusters, gravity holds things together while dark matter provides most of the mass. Within galaxies, gravity, magnetism, and stellar winds sculpt clouds of gas into new stars. Within stars, nuclear fusion creates energy and synthesizes elements. On planets, chemistry and geology and sometimes biology create complexity. This is the hierarchy of structure in the universe, each level built on the levels below, new properties and behaviors emerging at each level. The universe is organized, not chaotic, because the laws of physics favor certain stable structures. Stars, for instance, represent a balance between gravity pulling inward and pressure from nuclear fusion pushing outward. Planets form because gravity pulls matter together and angular momentum causes it to form disks. These processes are not deterministic in detail but statistical. We can't predict exactly where each star will form in a galaxy, but we can predict the overall rate of star formation, the distribution of stellar masses, the chemical evolution of the galaxy over time. We work with probabilities and averages, extracting patterns from apparent randomness. This is true at every level. We can't predict the exact position of an electron, but we can predict the probability distribution. We can't predict exactly when a specific radioactive atom will decay, but we can predict the half-life of a sample. We can't predict the weather more than about 10 days out, but we can predict climate trends over decades. The universe operates on many timescales simultaneously. Quantum fluctuations happen in tiny fractions of a second. Chemical reactions happen in milliseconds to hours. Ecological processes happen over years to centuries. Geological processes take millions of years. Stellar evolution takes billions of years. The expansion of the universe takes tens of billions of years. We humans, living 70 or 80 years if we're lucky, occupy a narrow slice of this vast range. We can barely perceive processes that take seconds and cannot directly perceive processes that take centuries. Yet through science, we've learned to understand processes from the incredibly fast to the incomprehensibly slow. We use technology to speed up or slow down time, to compress eons into computer simulations or stretch microseconds into observable data. This is one of the great achievements of human civilization. We've developed tools and techniques that vastly extend our senses and our understanding beyond our biological limitations. Telescopes let us see across billions of light years. Microscopes let us see individual atoms. Particle accelerators let us probe the subatomic realm. Computers let us simulate complex systems impossible to study directly. And we've done this in just a few thousand years of civilization, a tiny fraction of human history, an infinitesimal fraction of cosmic history. Imagine what we might understand in another 1,000 years, another 1,000,000 years, if we survive that long. The mysteries that seem intractable now might be solved. New mysteries we can't even conceive of might emerge. The universe has been revealing its secrets to us gradually, each discovery opening new questions. When we learned about atoms, we wondered what they were made of. Electrons, protons, neutrons. Then we wondered what protons and neutrons were made of. Quarks. Are quarks fundamental, or are they made of something smaller? We don't know yet. We keep finding new layers of structure, new levels of organization. Each time we think we've reached the bottom, we discover another layer beneath. Maybe this continues forever, turtles all the way down. Or maybe there really are fundamental building blocks, irreducible entities from which everything else is constructed. String theory suggests that strings are fundamental, that quarks and electrons and all other particles are different vibration modes of these strings. Loop quantum gravity suggests that space itself is made of discrete loops at the Planck scale, the smallest meaningful distance. These theories might both be aspects of some deeper theory we haven't discovered yet. The Planck scale represents a kind of ultimate limit. At distances smaller than the Planck length, about 10 to the minus 35 meters, quantum effects of gravity become significant. Space and time themselves might lose meaning at this scale. We can't build experiments that probe these tiny distances, at least not with current technology. The energies required are far beyond what our particle accelerators can achieve. But the early universe reached these energies naturally. In the first tiny fraction of a second after the Big Bang, the universe was so hot and dense that Planck-scale physics mattered. Understanding the very early universe requires understanding quantum gravity. This is why cosmology and particle physics are deeply connected. The largest structures in the universe and the smallest constituents of matter are linked through the Big Bang. This is the beauty of physics. Everything connects. The behavior of atoms determines the properties of materials, which determines what kinds of planets can form, which determines where life can arise. The lives and deaths of stars determine what elements exist, which determines what chemistry is possible, which determines what forms of life can evolve. The expansion rate of the universe determines how long stars will shine, which determines how long civilizations can potentially last. We're all connected, not just to each other but to the cosmos as a whole. Your existence depends on the nuclear reactions in stars, on the chemistry of early Earth, on the evolution of life over billions of years, on cosmic expansion allowing galaxies to form, on quantum mechanics determining how atoms behave. Change any of these, and you wouldn't exist. This is simultaneously humbling and empowering. Humbling because we're so small and contingent, dependent on countless factors beyond our control. Empowering because we're part of something so much larger, connected to the grandest processes in nature. We're not separate from the universe, observing it from outside. We're inside it, made of it, shaped by it, and shaping it in return through our actions. Every breath you take changes the atmosphere infinitesimally. Every decision you make sends ripples through the network of causation that connects all events. You are not a passive observer but an active participant in the unfolding of cosmic history. Your choices matter, not in some cosmic accounting but in their concrete effects on yourself and others. This is what gives life meaning despite the apparent indifference of the universe. We create meaning through our relationships, our projects, our values. We care about things, and that caring makes those things important, at least to us. The universe doesn't care whether you're happy, but you care, and the people who love you care. That's enough. In the end, we're storytelling creatures. We make sense of the world through narratives. Science is humanity's most successful story, one that corresponds closely to reality, that makes accurate predictions, that has given us power over nature. But it's not the only story that matters. There are stories of love and loss, courage and fear, hope and despair. There are personal stories and cultural stories, myths and histories, fictions that reveal truths about human nature. All of these stories matter because they shape how we understand ourselves and our place in the world. The cosmic story we've been telling is one such narrative. It's true, as far as we know, based on observation and reason. But it's also meaningful because it connects us to something larger than ourselves. It gives us perspective on our lives. our troubles, our triumphs. When you're worried about something trivial, remembering the cosmic scale can help you let it go. When you're facing something genuinely difficult, remembering that you're made of star stuff, that you're part of 13.8 billion years of cosmic evolution, can give you strength. You are the universe experiencing itself, and that's remarkable. So as you drift towards sleep, let these ideas settle into your mind. The vastness of space, the depth of time, the intricacy of the laws of nature, the emergence of complexity from simplicity, the story of how hydrogen, given enough time, becomes human. Rest now in the knowledge that you're connected to everything, that your atoms have been recycled through countless forms over billions of years, that you're a temporary configuration of matter that can think and feel and wonder. Rest knowing that the universe continues its slow evolution, indifferent yet filled with beauty, empty yet containing everything. The stars shine on, oblivious to your existence. But you know they exist. You can see them, understand them, appreciate them. And that knowledge, that understanding, that appreciation, that's a kind of miracle. Sleep well, fellow stardust. Tomorrow the cosmos will still be here, vast and mysterious and wonderful. And so will you, ready to experience another day of this improbable existence we call life. The universe gave you consciousness. Use it well. Make meaning. Create beauty. Seek truth. Love deeply. These things matter not to the cosmos, but to you. And you matter not to the cosmos perhaps, but to yourself and to others. That's enough. That's everything. The concept of infinity has haunted mathematicians and physicists for centuries. Is the universe infinite in extent, or does it have boundaries? Current observations suggest it's flat, which means it could extend infinitely in all directions. But we can only see a finite portion, limited by the speed of light and the age of the universe. Beyond our cosmic horizon lies more universe, perhaps infinitely more, forever beyond our ability to observe. If the universe is truly infinite, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if the arrangement of matter is random, then given infinite space, every possible configuration must occur somewhere. There would be infinite copies of Earth, infinite copies of you, living out every possible variation of your life. In some distant galaxy, there's another version of you making different choices, living a different life, dreaming different dreams. This idea feels absurd, yet it follows logically from an infinite universe and the finite number of ways particles can be arranged in any given volume. Infinity is strange. It breaks our intuitions, which evolved to deal with finite quantities. We can't truly grasp infinity, but we can work with it mathematically, and the mathematics suggests these bizarre possibilities. But perhaps the universe isn't infinite. Perhaps it wraps around on itself, like the surface of a sphere. You could travel in one direction and eventually return to your starting point, having circumnavigated the cosmos. The universe would be finite in volume but have no edge, no boundary. This is possible if space has positive curvature, though current measurements suggest space is flat or very nearly so. Or perhaps our universe is just one bubble in an infinite multiverse. Eternal inflation theory suggests that the inflating quantum fields that drove the Big Bang never completely stop inflating everywhere. Inflation ends in some regions, creating bubble universes like ours, but continues elsewhere, spawning more bubbles eternally. Each bubble would have its own Big Bang, its own physical constants, its own history. In this scenario, the multiverse is vastly larger than any individual universe, and most of it is forever beyond our reach. We're trapped in our bubble, separated from other bubbles by regions of space expanding faster than light. We could never visit another universe, never communicate with beings there, never even detect their existence directly. Yet the theory makes predictions we might be able to test. If our bubble universe collided with another during inflation, it might have left a signature in the cosmic microwave background, a circular pattern of temperature fluctuations. Searches have been conducted. No definitive signals have been found, but the search continues. The concept of a multiverse troubles some scientists. It seems to put ideas beyond the reach of experimental verification. If we can never observe other universes, Is the multiverse a scientific theory or a philosophical speculation? The debate continues. Some argue that if a theory makes testable predictions in our universe and implies a multiverse as a consequence, then the multiverse is a legitimate scientific idea. Others remain skeptical. These questions about the ultimate nature of reality might never be fully answered. We're limited by our position in space and time, by the speed of light, by the finite resolution of our instruments. There are questions science might never resolve, not because they're inherently unanswerable, but because the answers lie beyond our observational reach. But that doesn't mean we should stop asking. The history of science is filled with problems that seemed intractable but were eventually solved. Heavier-than-air flight was impossible until the Wright brothers did it. Splitting the atom was impossible until we split it. Landing on the moon was impossible until Neil Armstrong stepped onto its surface. We tend to underestimate what's possible given enough time and effort. 1,000 years ago, the idea that we'd understand the nuclear reactions powering the sun would have seemed like fantasy. 500 years ago, the idea that we'd detect gravitational waves from colliding black holes would have been incomprehensible. 50 years ago, finding thousands of planets around other stars seemed impossibly difficult. Yet we've done all these things. We've extended our senses and our understanding to encompass phenomena from the quantum realm to the cosmic horizon. We've learned to see in wavelengths our eyes can't detect, to observe objects our ancestors couldn't have imagined, to test ideas about the fundamental nature of reality. And we're just getting started. The questions we can't answer today might yield to future observations and theories. Or they might be replaced by better questions we haven't thought to ask yet. Science is not a static body of knowledge but a process, a way of questioning and investigating and updating our understanding based on evidence. Consider how much we've learned just in the last century. In 1924, we didn't know there were other galaxies. We thought the Milky Way was the entire universe. Then Edwin Hubble observed Cepheid variables in what we now know as the Andromeda Galaxy and proved it was a separate galaxy, millions of light years away. Overnight, the universe became vastly larger. In 1929, Hubble discovered that galaxies are moving away from us, with more distant galaxies moving faster. The universe is expanding. This was shocking. People had assumed the universe was static, eternal, unchanging. But Hubble's observations showed it had a history, that it was evolving over time. This discovery eventually led to the Big Bang theory. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background while trying to eliminate noise from a radio antenna. They found a persistent signal coming equally from all directions, the afterglow of the Big Bang. This discovery provided strong evidence for the Big Bang theory and gave us a snapshot of the universe when it was just 380,000 years old. In 1998, observations of distant supernovae revealed that the expansion of the universe is accelerating. This was completely unexpected. It implied the existence of dark energy, a mysterious component making up 68% of the universe. We still don't understand what dark energy is, but its discovery fundamentally changed our understanding of cosmology. In 2015, LIGO detected gravitational waves for the first time, confirming a prediction Einstein made a century earlier. This opened an entirely new way of observing the universe, allowing us to detect events we could never see with light. It was like gaining a new sense, like a deaf person suddenly hearing for the first time. These discoveries happened within living memory. People alive today remember when we didn't know about dark energy, when gravitational waves were theoretical, when exoplanets were speculative. The pace of discovery has been breathtaking, and there's no reason to think it will slow down. The next few decades promise more revelations. The James Webb Space Telescope is revealing the early universe in unprecedented detail. New gravitational wave detectors are being built that will be far more sensitive than current ones. The next generation of particle accelerators might discover new fundamental particles or reveal new physics beyond the standard model. We might detect biosignatures in the atmosphere of an exoplanet, providing the first evidence of life beyond Earth. We might detect a signal from an extraterrestrial civilization. We might solve the dark matter mystery, finally identifying what this invisible substance is. We might understand dark energy, resolving one of the deepest puzzles in cosmology. Or we might be surprised by something completely unexpected, some discovery that opens up entirely new questions. This has happened repeatedly throughout history. The most important discoveries are often the ones nobody predicted. Nature is more inventive than we are. Quantum entanglement, for instance, was discovered as a strange prediction of quantum mechanics that Einstein thought proved the theory was wrong. But experiments confirmed it was real. Particles can be correlated in ways that classical physics says shouldn't be possible. Measuring one particle instantaneously affects the other, regardless of distance. This doesn't allow faster-than-light communication, but it does show that the universe is fundamentally non-local in ways we still don't fully understand. Quantum computers are being built that exploit entanglement to perform certain calculations exponentially faster than classical computers. These machines might solve problems currently intractable, from simulating complex molecules for drug design to optimizing logistics networks to breaking current encryption schemes. They might also help us understand quantum mechanics better, allowing us to explore quantum phenomena that are too complex to calculate classically. Artificial intelligence is advancing rapidly, with systems now capable of tasks that seemed uniquely human just years ago. AI can generate realistic images and text, play complex games at superhuman levels, discover new mathematical theorems, predict protein structures. As AI systems become more capable, they might accelerate scientific discovery, finding patterns in data too complex for humans to discern, generating hypotheses we wouldn't think of, designing experiments optimally. But AI also raises profound questions. Can a machine be conscious? Can it truly understand, or is it just manipulating symbols according to rules without any inner experience? If we create artificial minds more intelligent than ourselves, what responsibilities do we have toward them? What rights might they have? These questions blend philosophy, ethics, and technology in ways we're only beginning to grapple with. The same technology that might help us understand the universe could also help us modify ourselves. Genetic engineering might allow us to eliminate diseases, extend lifespans, enhance cognitive abilities. Neural interfaces might allow direct communication between brains and computers. We might merge with our technology, becoming something post-human, neither fully biological nor fully artificial. These possibilities raise ethical questions with no easy answers. Should we modify human nature? What counts as therapy versus enhancement? Who decides what modifications are acceptable? How do we prevent inequality between those who can afford enhancements and those who can't? These questions will become increasingly urgent as the technology develops. But whatever we become, we'll still be asking questions about the universe and our place in it. Curiosity seems to be a deep feature of intelligence, perhaps necessary for any mind capable of understanding its environment. Even post-human intelligences would presumably want to understand reality, to explore the cosmos, to seek answers to fundamental questions. The universe might be teeming with such intelligences at various stages of development. Some might be far older and more advanced than us. Others might be younger, just discovering fire or agriculture. And most might be at intermediate stages, grappling with the same questions we face about technology, society, and their place in the cosmos. If we encounter another intelligence, whether biological or artificial, whether from Earth or elsewhere, it will be one of the most significant moments in history. We'll learn how contingent or inevitable our path has been. We'll see what other solutions evolution or engineering have found to the problem of survival and understanding. We'll no longer be alone in our questioning. But even if we never encounter another intelligence, we're not truly alone. We're connected to the cosmos through the atoms in our bodies, through the light reaching our eyes from distant stars, through the gravitational influence of distant galaxies on our local motion through space. We're embedded in the universe, inseparable from it. Every breath you take contains atoms that were once part of other people, other organisms, scattered across the planet by atmospheric mixing. You're breathing atoms that Julius Caesar breathed, that dinosaurs breathed, that ancient bacteria released into the early atmosphere. You're intimately connected to all of Earth's history. And Earth itself is connected to cosmic history. The planet formed from debris left over from the Sun's formation. That debris came from previous generations of stars. Those stars formed from gas clouds enriched by even earlier stars. Following the chain back, all the atoms in your body trace back to the Big Bang, either as primordial hydrogen and helium or as elements forged in stellar cores and dispersed by supernovae. You are, quite literally, a way for the universe to know itself. Through your eyes, the cosmos observes its own grandeur. Through your mind, it contemplates its own nature. This is not poetry or metaphor. It's a straightforward consequence of physics and biology. You are a localized concentration of matter and energy, organized in such a way as to produce consciousness, thought, self-awareness. The improbability of your existence is staggering. The chain of events leading to you being here, reading these words, stretches back billions of years. Any break in that chain and you wouldn't exist. Your parents had to meet. Their parents had to meet. Going back, your ancestors had to survive countless dangers, plagues, famines, wars. Going back further, the primates that became humans had to avoid extinction. Going back further still, the asteroid that killed the dinosaurs had to hit, clearing ecological space for mammals to diversify. Going back to the formation of Earth, the planet had to form in the habitable zone, had to have the right size and composition, had to acquire water and an atmosphere. Going back to the formation of the Sun, the gas cloud it formed from had to have the right mix of elements, enriched by previous stars. Going back to the first stars, the early universe had to have the right density fluctuations to allow structure to form. Going back to the Big Bang, the fundamental constants of physics had to have the right values to allow atoms, stars, and galaxies to exist. Change any of these constants slightly and the universe would be radically different, perhaps sterile, incapable of supporting life or any complex structures. This apparent fine-tuning troubles some people. It seems to suggest design, purpose, intention. But there are naturalistic explanations. If there's a multiverse with varying constants, we necessarily find ourselves in a universe capable of supporting observers. We couldn't exist in a universe incompatible with our existence. This anthropic reasoning explains the apparent fine-tuning without invoking a designer. Or perhaps the constants aren't as finely tuned as they appear. Some calculations suggest that varying multiple constants simultaneously opens up larger regions of parameter space compatible with life. Life might be more robust, less contingent on precise values, than we initially thought. Or perhaps life doesn't require the same physics we have. Maybe there are forms of organization, patterns that can reproduce and evolve, that don't rely on chemistry as we know it. Maybe stars and galaxies themselves are alive in some abstract sense, patterns that maintain themselves and replicate. This is highly speculative, but it reminds us that our understanding of life is limited by the single example we know, Earth's biology. We define life by characteristics like reproduction, metabolism, evolution, response to stimuli. But these are properties of Earth life. Alien life might work differently. It might not have cells or DNA. It might not be carbon-based. It might exist in environments we consider incompatible with life, in the cores of stars or the event horizons of black holes or the quantum foam of spacetime itself. This sounds like science fiction, but we should remain open-minded. The universe has surprised us repeatedly. Every time we've assumed something was impossible, nature has shown us otherwise. Life in deep-sea vents where sunlight never reaches. Microbes surviving in Antarctic ice. Organisms thriving in nuclear reactors, in highly acidic or alkaline environments, in the stratosphere, in solid rock miles underground. Life is tenacious, adaptable, resourceful. It finds ways to survive and reproduce in almost any environment that provides energy and raw materials. Given the abundance of planets, the ubiquity of organic molecules, the versatility of chemistry, it would be surprising if life were unique to Earth. But intelligence might be rare. Life existed on Earth for over 3 billion years before anything resembling intelligence appeared. For most of Earth's history, the most complex organisms were single-celled. Multicellular life is relatively recent, appearing only about 600 million years ago. Complex brains are even more recent. humans, with our capacity for language, abstract thought, and culture, have existed for just a few 100,000 years. Intelligence might not be inevitable. Evolution doesn't have goals or direction. It's not progressing toward anything. It's simply the differential survival and reproduction of organisms in their environments. Intelligence happened to be advantageous for our ancestors, but in most environments, it might not be worth the metabolic cost. Brains are expensive, requiring large amounts of energy. Most organisms get by fine without them. So while simple life might be common in the universe, intelligent life might be rare. We might be one of very few civilizations in the galaxy, or even the only one. This would make us incredibly special, custodians of something precious and fragile. It would increase our responsibility to survive, to spread, to ensure intelligence doesn't vanish from this region of space. But loneliness isn't necessarily a bad thing. It would mean the galaxy is ours to explore, to settle, to fill with life and thought. We wouldn't have to worry about hostile aliens or competing civilizations. We could take our time, spreading gradually, carefully, ensuring we don't repeat the mistakes of colonialism and exploitation that mar human history. A mature spacefaring civilization would hopefully have outgrown tribalism, nationalism, the us versus them thinking that has caused so much suffering. When you can see Earth as a tiny blue dot from space, borders seem arbitrary. When you understand we're all made of the same atoms, all products of the same evolutionary process, all inhabitants of the same cosmic moment, divisions based on nationality or ethnicity or religion seem petty. This is one gift the cosmic perspective offers. It contextualizes our differences, revealing them as superficial variations on a common theme. We're all human, all Earthlings, all made of star stuff. Our commonalities vastly outweigh our differences. The things that unite us are far more fundamental than the things that divide us. Yet we continue to fight, to compete, to hoard resources, to prioritize short-term gains over long-term survival. We know climate change threatens civilization, yet collective action remains inadequate. We know nuclear weapons could end humanity, yet thousands remain on hair-trigger alert. We know pandemics will happen, yet we underfund preparedness. We know asteroids could strike Earth, yet we barely monitor them. These aren't unsolvable problems. We have the knowledge and technology to address them. What we lack is will, coordination, long-term thinking. We're still operating with cognitive and social systems that evolved for small tribal groups, not global civilization. Our instincts lead us astray when applied to problems at planetary scale. But we can adapt. We can learn to think long-term, to cooperate globally, to make decisions based on evidence rather than emotion or ideology. We've done it before. The eradication of smallpox required global cooperation. The Montreal Protocol successfully addressed ozone depletion. The International Space Station is a product of multiple nations working together. We can solve collective action problems when we choose to. The question is whether we'll make that choice before it's too late. The next few decades are crucial. The decisions we make now will echo for centuries or millennia. We could destroy ourselves or damage Earth so severely that recovery takes millions of years. Or we could transition to a sustainable civilization, one that could last as long as the sun shines, billions of years into the future. The universe doesn't care which path we take. But we should care. We're the only part of the universe that can care, at least in this region of space. We're the universe's way of caring about itself. And that gives us responsibility. We're at a unique moment in cosmic history. For billions of years, Earth was lifeless. For billions more, it hosted only simple organisms. For hundreds of millions of years, it had complex life but no intelligence. For hundreds of thousands of years, it had intelligence but no technology. Only in the last few thousand years have we had civilization. Only in the last few hundred years have we had science. Only in the last few decades have we had the power to significantly alter our planet or potentially spread beyond it. We're transitioning from a planet-bound species to a potentially space-faring one. We're developing technologies that could ensure our survival for eons or destroy us within years. We're at a critical juncture, a moment that will determine whether intelligence in this part of the universe flourishes or vanishes. The stakes couldn't be higher. We're playing for keeps, not just for our generation but for all future generations, for the potential of billions of years of human history yet to unfold. Every choice we make ripples forward through time, affecting people not yet born, shaping the world they'll inherit. This should fill us with both humility and determination. Humility because we're so small, so recent, so uncertain in our knowledge. Determination because despite our limitations, we have the power to shape the future. We're not passive observers but active participants in cosmic evolution. The atoms in your body will outlast you. They'll be recycled into other forms, other organisms, other structures. In a sense, you're immortal, not as an individual but as a collection of atoms that have existed since shortly after the Big Bang and will exist until the heat death of the universe. You're a temporary pattern, a brief organization of matter that can think and feel, arising from and returning to the cosmic cycle of birth and death and rebirth. This might sound depressing, but it's actually liberating. You're part of something vast and ancient and enduring. Your individual existence is finite, but you're connected to something infinite. You're a wave in an ocean, distinct for a moment but made of the same water, returning eventually to the whole. Buddhism teaches that suffering comes from attachment, from clinging to impermanent things as if they were permanent. The cosmic perspective reinforces this wisdom. Everything changes. Stars are born and die. Galaxies merge and disperse. Even atoms eventually decay. Nothing lasts forever. Accepting this impermanence can free us from anxiety about loss and death. Yet this doesn't mean nothing matters. Even temporary things can have value, can create meaning, can be worth preserving and celebrating while they last. A beautiful sunset is no less beautiful for being brief. A loving relationship is no less meaningful for being finite. Life itself is more precious because it's temporary. This is the paradox at the heart of existence. We matter and we don't matter. Our lives are significant and insignificant. We're central to our own experience but peripheral to the cosmos. Both perspectives are true. We need to hold them simultaneously, to remember the vastness of the universe while also honoring the intimacy of our daily lives. The stars above remind us of the big picture. But the people around us remind us that meaning happens at human scale, in conversations and relationships, in small acts of kindness and moments of connection. These things don't show up in physics equations or astronomical observations, but they're no less real for that. The universe contains multitudes. It contains galaxy clusters and subatomic particles, black holes and quantum fluctuations, cosmic voids and DNA molecules. It contains your thoughts and feelings, your memories and dreams, your fears and hopes. All of this is part of the universe, all of it equally real, all of it woven into the vast tapestry of existence. So as sleep approaches, let yourself relax into this interconnectedness. You're not separate from the universe but part of it, temporarily organized into human form but ultimately inseparable from the whole. Your consciousness is a gift, a brief flowering of awareness in an otherwise unconscious cosmos. Use it well while you have it. Tomorrow you'll wake to another day, another chance to experience this improbable existence. You'll see sunlight, breathe air, eat food, interact with other conscious beings. These ordinary miracles happen every day, so common we forget how extraordinary they are. But from a cosmic perspective, they're anything but ordinary. You live on a planet with liquid water, breathable atmosphere, protective magnetic field, orbiting a stable star in the habitable zone, in a galaxy old enough to have produced heavy elements, in a universe whose laws permit complexity and consciousness. The odds against this are astronomical, yet here you are. Don't take it for granted. Don't waste this precious time worrying about things that won't matter in a year, in a decade, in a century. Focus on what matters, what brings joy and meaning and connection. Love deeply, think clearly, act courageously, create beauty. These are the things that make life worth living, that justify the universe's long labor in creating conscious beings. The cosmos gave you this moment. What you do with it is up to you. Sleep now, rest, and wake tomorrow ready to make the most of another day in this vast, ancient, mysterious, beautiful universe we call home. The phenomenon of time dilation reveals how elastic our universe truly is. When objects move at speeds approaching light, time itself slows down for them relative to stationary observers. This isn't illusion or perception, it's physical reality confirmed by atomic clocks on aircraft and satellites. A twin traveling near light speed would age more slowly than their sibling remaining on Earth. Upon return, the traveler might have experienced only a few years while decades passed on Earth. Gravity also warps time. Clocks tick more slowly in stronger gravitational fields. On the surface of a neutron star, time passes noticeably slower than in empty space. Near a black hole's event horizon, time dilation becomes extreme. An astronaut falling toward a black hole would experience time normally from their perspective, but to an outside observer, they would appear to slow down asymptotically, never quite reaching the horizon, their image frozen and redshifted into invisibility. This means time isn't universal. There's no cosmic clock ticking away the same seconds for everyone. Each observer has their own proper time. And these times only align when observers are stationary relative to each other in the same gravitational field. The universe has no absolute now, no universal present moment. Events that are simultaneous for one observer occur at different times for another moving observer. This relativity of simultaneity demolishes our intuitive notion of time as a universal river flowing at constant rate. Instead, space-time is a four-dimensional manifold where each observer carves out their own particular slice as now. Your present moment is different from the present moment of someone moving past you at high speed, even though you occupy the same location in space. These aren't just theoretical curiosities. GPS satellites must account for both special relativistic effects from their orbital velocity and general relativistic effects from Earth's weaker gravity at altitude. Without these corrections, GPS would accumulate errors of kilometers per day. Your navigation app works because physicists understand how time bends. The malleability of space-time suggests possibilities that seem like fantasy. Wormholes, if they exist and can be stabilized, would be tunnels through space-time connecting distant regions. You could enter one mouth and exit the other instantly, having bypassed the space in between. This doesn't violate relativity because you're not traveling faster than light through space, you're taking a shortcut through a higher dimension. Theoretical physics permits wormholes as solutions to Einstein's equations, but creating and stabilizing them would require exotic matter with negative energy density. We've never observed such matter, though quantum fields can have negative energy in certain configurations through the Casimir effect. Whether this scales up to macroscopic wormholes remains unknown. Time travel presents even more exotic possibilities and paradoxes. Some solutions to Einstein's equations permit closed time-like curves, paths through spacetime that loop back to their starting point in time. You could potentially travel to your own past. But this creates logical contradictions. What if you prevented your own birth? This is the grandfather paradox, and it suggests either time travel is impossible, or reality somehow prevents paradoxes, or the many worlds interpretation is correct and changing the past creates a new timeline branching from the original. Physicist Kip Thorne showed that if wormholes exist, they could be converted into time machines. Move one mouth of the wormhole at high speed and return it. Due to time dilation, less time will have passed for the moving mouth than the stationary one. Now the two mouths exist at different times. Step through one mouth and emerge from the other in the past. But you can only travel back to when the time machine was created, not before. No dinosaur safaris, unfortunately. Causality seems fundamental to how the universe operates, yet quantum mechanics hints at its limitations. Quantum entanglement creates correlations between particles that seem to involve backwards causation. When you measure an entangled particle, its partner instantly takes on a correlated state, regardless of distance. Einstein called this spooky, but experiments confirm it happens. The resolution is that no information travels faster than light, so causality isn't violated, but the mechanism remains deeply puzzling. Some interpretations suggest quantum effects literally do involve retrocausality, with future measurements affecting past states. The delayed choice quantum eraser experiment seems to show this. though interpretations vary. Perhaps cause and effect aren't as straightforward as we assume. Perhaps the universe is more like a self-consistent mathematical structure where past and future mutually determine each other. The arrow of time, the fact that we remember the past but not the future, that eggs break but don't spontaneously reassemble, derives from thermodynamics. Entropy, the measure of disorder, increases over time in closed systems. This gives time a direction. But the fundamental laws of physics are time-symmetric. They work equally well forwards or backwards. The arrow of time emerges from statistics. From the fact that there are vastly more disordered states than ordered ones. Why did the universe begin in such a low entropy state? The Big Bang was incredibly ordered compared to what came later. This initial condition is crucial for the arrow of time, but we don't understand why the universe started that way. It's one of the deepest mysteries in cosmology. Without that initial low entropy, there would be no arrow of time, no distinction between past and future, no evolution or change, no memory or history. Some physicists speculate that the Big Bang wasn't the true beginning, that our universe emerged from a previous contracting phase that reached maximum density and bounced. This cyclic model avoids the initial singularity and might explain the low initial entropy, though it faces challenges in matching observations. Other models invoke quantum fluctuations creating the universe from nothing, though nothing in quantum mechanics is far from what we usually mean by the word. The vacuum of space, even with all particles removed, seethes with virtual particles constantly appearing and disappearing, borrowing energy from the uncertainty principle, and repaying it so quickly we can't detect them directly. But we can detect their effects. The Casimir effect, where two metal plates in vacuum attract each other due to virtual particles having less room between the plates than outside, demonstrates this quantum vacuum is real and has measurable consequences. These virtual particles might have contributed to cosmic inflation. Quantum fluctuations in the inflaton field, the hypothetical field driving inflation, would be stretched by the rapid expansion and become the seeds of cosmic structure. The galaxies, stars, and ultimately you trace back to quantum uncertainty, to the inherent fuzziness of reality at the smallest scales. Heisenberg's uncertainty principle states that you cannot simultaneously know both position and momentum of a particle with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This isn't about measurement limitations but reflects something fundamental about reality. Particles don't have definite positions and momenta simultaneously. These properties are complementary, like wave and particle aspects of light. Wave-particle duality confounded early quantum physicists. Light behaves as a wave in some experiments, showing interference and diffraction, but as particles, photons, in others, like the photoelectric effect. Eventually, they realized this wasn't paradox but limitation of classical concepts. Light is neither wave nor particle but something more fundamental that exhibits both behaviors depending on how you observe it. The same applies to matter. Electrons, protons, even large molecules exhibit wave-like interference. We've demonstrated interference patterns with molecules containing hundreds of atoms. In principle, even you have a wavelength, though it's so incredibly tiny as to be utterly unmeasurable. The boundary between quantum and classical behavior isn't sharp but gradual, with quantum effects becoming negligible for large objects. Why the quantum world transitions to the classical world we experience remains debated. Decoherence, the interaction of quantum systems with their environment, destroys quantum superpositions extremely rapidly for macroscopic objects, making them behave classically. A single air molecule colliding with a dust particle is enough to collapse its quantum state. This explains why we don't see quantum weirdness in everyday life, but whether it fully resolves the measurement problem remains controversial. The measurement problem asks, what counts as a measurement? When exactly does the quantum wave function collapse from superposition to definite state? Standard quantum mechanics doesn't specify. Consciousness doesn't seem necessary. Measuring devices work just fine. But where's the boundary? These questions connect to deep issues about the nature of reality and observation. Some physicists, like John Wheeler, suggested the universe might be participatory, that observers play a role in bringing reality into being through observation. His delayed choice experiment showed that decisions made now can seemingly affect what happened in the past, at least regarding wave or particle behavior of photons. This doesn't quite mean consciousness creates reality, but it suggests observation and reality are more entangled than classical physics implies. Quantum mechanics has been called the most successful theory in physics. Its predictions have been confirmed to incredible precision. The anomalous magnetic moment of the electron agrees with quantum electrodynamics calculations to 11 decimal places. No other theory approaches this level of accuracy. Yet we still argue about what it means, what it tells us about the nature of reality. Perhaps reality is fundamentally probabilistic, and determinism is the illusion. Perhaps the universe doesn't have definite properties independent of measurement. Perhaps observation doesn't reveal pre-existing reality but participates in creating it. These ideas clash with classical intuitions, but nature doesn't care about our intuitions. It is what it is, regardless of what seems reasonable to beings whose brains evolved to track predators and find food. Our cognitive evolution optimized us for survival in the African savanna, not for understanding quantum mechanics or cosmology. That we can understand these things at all is remarkable. Mathematics gives us tools to extend our thinking beyond intuition, to follow logical implications into realms where intuition fails. We can't visualize 10-dimensional string theory or quantum superposition, but we can calculate with them, make predictions, test them against observations. This power of abstract thought, this ability to transcend our evolutionary limitations through reason and mathematics, might be the most impressive feature of human intelligence. We're not just clever apes. We're beings capable of understanding our own origins, our place in the cosmos, the laws governing reality itself. No other species on Earth, possibly no other species in the galaxy, has achieved this. Language played a crucial role. It allowed us to share knowledge, to build on previous generations' discoveries, to develop culture and science. A single human alone couldn't understand quantum mechanics or general relativity. These achievements required thousands of people over centuries, each contributing small pieces, building a collective understanding far exceeding any individual's capacity. Science is a social enterprise, a collaborative effort to understand reality. Individual scientists make mistakes, have biases, sometimes commit fraud. But the scientific community as a whole corrects these errors through replication, peer review, and ongoing testing. False ideas eventually get filtered out. True ideas, even initially rejected ones, eventually win acceptance if evidence supports them. Continental drift was rejected for decades until plate tectonics explained the mechanism. Heliocentrism was rejected until telescopes confirmed Jupiter's moons orbited Jupiter, not Earth. Quantum mechanics was rejected by many, including Einstein, until experiments confirmed its predictions. Science is self-correcting, though the process can be slow and messy. This gives us reason for optimism about humanity's long-term understanding. We're still ignorant about most things, dark matter and dark energy especially, but we're less ignorant than a century ago, vastly less than a millennium ago. The trend is toward greater understanding, even as each answer reveals new questions. Some questions might have no answers, or answers beyond our capacity to comprehend. A dog can't understand calculus no matter how well you explain it. Its brain lacks the necessary architecture. Similarly, some aspects of reality might be literally incomprehensible to human minds, requiring cognitive capacities we don't possess. This is a humbling possibility, but not a reason to stop trying. Even with limitations, we've accomplished remarkable things. We've extended human lifespans, eliminated diseases, created technologies our ancestors would consider magical, explored our solar system with robots, and begun to understand the universe's origin and fate. We've taken atoms forged in stars and organized them into computers, spacecraft, medicines, art. Art deserves mention. Science isn't the only way humans make sense of the world. Art, music, literature, philosophy all provide frameworks for understanding human experience. A poem can capture truths about love or loss that scientific analysis misses. A painting can convey emotions beyond words. Music can produce experiences that brain scans barely begin to explain. These humanistic ways of knowing complement scientific ones. We need both. Pure science without humanistic wisdom leads to technologies deployed without consideration of consequences. Pure humanism without science leads to superstition and failure to understand nature. The ideal civilization would integrate both, using science to understand how the world works and humanism to decide what we should do with that knowledge. Such integration seems increasingly necessary as our technological power grows. We can now modify our own genomes, create artificial intelligences, potentially alter Earth's climate deliberately. These godlike powers require wisdom to wield responsibly. Our ancestors could damage their local environment but couldn't affect the planet as a whole. We can. This demands a level of collective maturity and foresight our species hasn't demonstrated consistently. Yet there are encouraging signs. International cooperation on science is strong. The Large Hadron Collider involves thousands of physicists from dozens of countries. Climate science is inherently international. The International Space Station hosted crews from multiple nations working together peacefully in orbit. When we focus on shared goals rather than tribal conflicts, we can accomplish remarkable things. Perhaps the cosmic perspective can help foster this cooperation. When you see Earth from space, a fragile blue marble in the darkness, borders become invisible. When you understand we're all made of star stuff, all products of the same cosmic evolution, divisions based on nationality or ethnicity seem arbitrary. We're one species on one planet, sharing a common origin and common fate. This doesn't erase cultural differences or individual identities. Diversity remains valuable. But it provides overarching unity, a shared identity as Earthlings, as humans, as conscious beings in a vast unconscious cosmos. This identity transcends narrower ones without eliminating them. You can be proudly American or Chinese or Brazilian while also being proudly human. The Voyager 1 spacecraft, now over 20 billion kilometers from Earth, carries a golden record with sounds and images representing Earth's diversity. Music from different cultures, greetings in dozens of languages, images of humans and landscapes. It's a message in a bottle, cast into the cosmic ocean, unlikely to ever be found but representing humanity's hope that we're not alone. If extraterrestrials find it millions of years from now, they'll discover a species capable of both beauty and violence, creativity and destruction. They'll find recordings of Bach and Chuck Berry, images of buildings and babies, greetings and languages that will likely be extinct. They'll learn about a civilization that existed briefly, that reached out across the stars despite knowing the chances of contact were vanishingly small. What would they make of us? Would they understand our music, our art, our messages? Or would it all be incomprehensible to minds shaped by completely different evolutionary pressures? We can't know. But the attempt matters. It demonstrates that we're a species that wonders, that reaches beyond immediate survival needs, that creates meaning and beauty for their own sakes. These uniquely human qualities, our art and science and philosophy, our capacity for wonder and creation, might be our most important contribution to the universe. We take raw matter and energy and organize them into forms with meaning and purpose. We create order from chaos, at least temporarily, at least locally, even as the universe trends toward maximum entropy. This fight against entropy defines life. Every organism maintains its organization by increasing disorder in its environment. You stay alive by eating ordered molecules, food, and excreting disordered ones, waste. You maintain your body's structure by constantly using energy, fighting against the tendency toward equilibrium and decay. When you die, your body's organization breaks down, entropy increases, and your atoms return to simpler arrangements. But while you live, you're a localized decrease in entropy, an island of order in a sea of chaos. And conscious life goes further, creating not just biological order but conceptual order. We organize information, create knowledge, build models of reality. Libraries and databases and scientific papers are all structures of information fighting against disorder, preserving understanding against the tendency toward forgetting and confusion. Civilization itself is an entropic anomaly, a vast structure of organization spanning billions of people, accumulating knowledge over thousands of years, growing more complex over time even as the universe as a whole grows more disordered. This can only happen because we're not a closed system. We're constantly drawing energy from the sun, using that energy to build and maintain our civilization's organization. When the sun dies, humanity, if it still exists, will need another energy source. We'll need to harness other stars, or tap into more exotic sources like black hole rotation or vacuum energy. A truly advanced civilization might persist even in the far future, clustering around the last energy sources, using every possible trick to extract usable energy from an increasingly cold and dark universe. Freeman Dyson calculated that a sufficiently efficient civilization could persist indefinitely even as the universe expands and cools, by going into hibernation for increasing periods, waking briefly when enough energy accumulates, then sleeping again. Total subjective time experience would be infinite even though the civilization operates for finite total time. This depends on protons being stable though. If protons decay, as some theories predict, this strategy fails. In the extreme far future, after the last black holes evaporate, after even protons have decayed if they do, what remains? Perhaps only photons, electrons, positrons, and neutrinos, spreading ever thinner as space expands. The temperature approaches absolute zero. Nothing happens. No structure, no change, no information processing. This is heat death, maximum entropy, the final equilibrium. Or perhaps quantum fluctuations eventually create new regions of inflation, new universes budding off from the void. Perhaps this has happened before. Perhaps our universe is just the latest in an eternal sequence, each one arising, expanding, cooling, ending, with new ones constantly appearing. Eternity might be filled with universes, each one brief compared to the infinite time span, but constantly renewed. These speculations push beyond what we can observe or test. They're more philosophy than science, informed by physics but not constrained by current data. Yet thinking about them helps us understand our place in the largest possible context, the ultimate fate of everything, the deepest nature of existence itself. For now, we live in a universe that's neither too young nor too old, where stars still shine, where planets harbor life, where intelligence has emerged and begun to understand its cosmic context. This epoch won't last forever, but it's lasting long enough for us to exist, to think, to wonder. That's enough. That has to be enough. Sleep comes gradually, consciousness fading as neural patterns shift, as your brain processes the day's experiences, consolidating memories, weakening synapses you didn't use, strengthening ones you did. Dreams emerge, strange narratives assembled from memory fragments and random neural firing, experiences that feel real while they last but evaporate upon waking. What is the function of dreams? We still don't entirely understand. Perhaps they help process emotions, or practice threat scenarios, or consolidate learning. Perhaps they're simply noise, the brain's idle mode, meaningless patterns we retrospectively narrate into stories. Or perhaps they serve multiple functions, with different types of dreams doing different things. REM sleep, when most vivid dreams occur, appears essential for memory consolidation and emotional regulation. Deprive someone of REM sleep and their cognitive function deteriorates. Rats die if completely prevented from sleeping. Sleep isn't optional for complex brains. It's a fundamental biological requirement, as necessary as food or water. Yet we spend a third of our lives unconscious, vulnerable, not responding to our environment. This seems maladaptive. Sleep must provide benefits that outweigh these substantial costs. The leading theory is that sleep allows the brain to perform maintenance, clearing out metabolic waste products that accumulate during waking, consolidating memories, pruning unnecessary neural connections. Your brain is incredibly active right now even as you sleep, perhaps as active as during waking. Blood flow actually increases to many brain regions during REM sleep. Your eyes move rapidly beneath closed lids, tracking dream imagery your visual cortex generates. Your body becomes paralyzed except for breathing and eye muscles, preventing you from acting out dreams physically. Occasionally this paralysis fails, causing REM behavior disorder where people physically enact their dreams, sometimes violently. Or it persists into waking, causing sleep paralysis where you wake unable to move, often accompanied by hallucinations. These glitches reveal how complex sleep is, how many systems must coordinate properly. As you drift deeper, thoughts become less coherent, more associative, less constrained by logic. This is the hypnagogic state, the boundary between waking and sleep, where strange insights sometimes emerge, where creative connections form between disparate ideas. Salvador Dali would hold a key over a metal plate, using the clang when he dropped it as he fell asleep to wake himself, capturing these hypnagogic visions. Soon you'll cross fully into sleep, descending through progressively deeper stages, your brain waves slowing, your body relaxing completely. You'll cycle through these stages multiple times tonight, spending most time in REM sleep and light stages in the later cycles toward morning. You'll dream perhaps 4 or 5 times, remembering only the last dream if any. And while you sleep, the universe continues its eternal dance, utterly indifferent to your momentary unconsciousness, to your existence, to anything happening on this planet or any other. Stars fuse hydrogen into helium. Black holes devour matter. Galaxies collide. Space expands. All according to mathematical laws, without purpose or intention, simply following the consequences of initial conditions and physical constants. Yet here you are, a tiny part of that indifferent universe, capable of caring, of finding meaning, of experiencing beauty and wonder. That's the miracle, that's the gift, that's what makes existence worthwhile despite its inevitable end, despite the universe's vastness and our relative insignificance. The concept of emergence reveals how complexity arises from simplicity through layers of organization. Individual neurons firing in your brain follow simple electrochemical rules, yet billions of them interact and create consciousness, memory, emotion, thought. No single neuron understands language or experiences love, yet the collective produces both. This is emergence, where the whole becomes genuinely more than the sum of its parts. Water molecules individually have no property of wetness. Wetness emerges only when trillions of molecules interact. A single water molecule cannot flow, freeze, or form waves. These properties exist only at the collective level. Similarly, life emerges from chemistry, consciousness emerges from neurons, economies emerge from individual transactions, ecosystems emerge from species interactions. The universe itself appears to be a hierarchy of emergent phenomena. Quarks combine to form protons and neutrons, which combine to form atomic nuclei, which capture electrons to form atoms, which bond to form molecules, which organize into cells, which cooperate to form organisms, which gather into societies. Each level has properties and behaviors that cannot be predicted from studying the level below in isolation. This suggests that understanding requires studying systems at multiple scales simultaneously. You cannot fully understand an organism by only studying its molecules, nor only by studying its ecology. Both perspectives provide essential insights. The challenge is integrating these different levels of description into coherent wholes. Reductionism, the strategy of understanding things by breaking them into components, has been spectacularly successful. We've reduced matter to elementary particles, biology to chemistry, chemistry to physics. But reductionism has limits. Knowing every particle's position and momentum in your brain wouldn't tell you what you're thinking. The information exists at a higher organizational level. Some scientists argue for emergence as a fundamental principle, suggesting that novel properties genuinely arise at higher levels of organization that are not present in or predictable from lower levels. Others maintain that emergence is epistemic rather than ontological, that higher-level properties could in principle be derived from lower-level ones given sufficient computational power, even if practically we cannot perform such derivations. This debate matters for understanding consciousness. If consciousness is strongly emergent, arising from neural organization in ways not reducible to physics, then artificial intelligence might never achieve true consciousness no matter how sophisticated its computations. If consciousness is weakly emergent or not emergent at all, then sufficiently complex information processing should produce it regardless of substrate. We don't know which view is correct. We don't even know how to test it definitively. Consciousness remains stubbornly resistant to explanation. We can correlate brain states with experiences, identify which neurons fire when you see red or feel pain, but correlation isn't explanation. The hard problem persists, the question of why physical processes produce subjective experience at all. Philosopher David Chalmers distinguished between easy and hard problems of consciousness. Easy problems, despite the name, include explaining how the brain processes information, integrates sensory inputs, produces behavioral outputs. These are just hard in the ordinary sense, requiring detailed neuroscience but not presenting conceptual mysteries. The hard problem is why there's something it's like to be you, why consciousness exists at all rather than just unconscious information processing. Some philosophers argue the hard problem is pseudo-problem, that once we fully explain the easy problems, nothing will remain to explain. Consciousness is just what information processing feels like from the inside. Others insist an explanatory gap remains, that no amount of third-person objective description will capture first-person subjective experience. These positions seem irreconcilable. Perhaps the question itself is malformed. Perhaps asking why physical processes produce consciousness is like asking why bachelors are unmarried. The answer might be definitional rather than causal. Systems that process information in certain complex self-referential ways just are conscious, by definition. Consciousness isn't produced by information processing, it is a particular type of information processing viewed from the inside. This functionalist view faces challenges though. The Chinese room thought experiment asks us to imagine someone following rules to manipulate Chinese symbols without understanding Chinese. From outside, the system appears to understand, producing appropriate responses to Chinese inputs. But does anything in the system actually understand Chinese? The person doesn't, they're just following rules. The rules don't, they're just abstract patterns. Where does understanding reside? Defenders of functionalism argue the system as a whole understands, even if individual components don't. Critics say this demonstrates that functional equivalence isn't sufficient for consciousness, that there's something more to understanding than input-output behavior. The debate continues, unresolved after decades. Integrated information theory proposes that consciousness corresponds to integrated information, a mathematical quantity measuring how much a system is more than the sum of its parts. High integrated information means consciousness. This theory makes predictions we can test, at least in principle, though measuring integrated information in real brains remains challenging. Global workspace theory suggests consciousness arises from a global workspace in the brain where information from different modules becomes available to the whole system. Unconscious processing happens in specialized modules working in parallel. Conscious experience occurs when information enters the global workspace, broadcasting to all modules. This explains why we can only consciously attend to one thing at a time despite massive parallel unconscious processing. These theories aren't necessarily contradictory. They might describe different aspects of consciousness, different necessary conditions that together are sufficient. Consciousness might require both integration of information and global broadcasting, along with other properties we haven't identified yet. The evolution of consciousness presents its own mysteries. At what point did consciousness arise? Are fish conscious? Insects? Single-celled organisms? We have no way to know for certain. We can identify behaviors suggesting consciousness, like flexible learning and novel problem-solving, but behavior is always ambiguous. Sophisticated behavior could arise from unconscious mechanisms. Most neuroscientists assume consciousness requires complex nervous systems, probably excluding insects and definitely excluding bacteria. But we're uncertain. Some organisms with tiny nervous systems, like bees with fewer than 1 million neurons compared to our 86 billion, demonstrate impressive cognitive abilities. They navigate using mental maps, communicate through symbolic dances, solve novel problems. Are they conscious? We don't know. The question matters for ethics. If animals are conscious, capable of suffering, we have moral obligations toward them. The worse their suffering, the stronger our obligations. But measuring suffering in other species is difficult. Do fish feel pain the way mammals do? Their nervous systems differ significantly from ours. Some scientists argue fish lack the neural structures necessary for conscious pain. Others point to behavioral evidence suggesting they do experience something akin to pain. We struggle to determine consciousness in other humans sometimes. Patients in minimally conscious states or locked-in syndrome might be fully conscious but unable to communicate. New brain imaging techniques reveal some vegetative patients are conscious, responding to questions through measured brain activity even though they cannot move or speak. How many conscious patients have we misclassified over the years? These difficult cases reveal how much we depend on communication for recognizing consciousness. Without behavioral evidence, we're uncertain. A person in a coma, an octopus, an alien intelligence, we struggle to recognize consciousness without familiar signals. This suggests our understanding remains superficial, tied too closely to human specifics rather than grasping consciousness in general. Octopuses present a fascinating case. They evolved intelligence independently from vertebrates. Their last common ancestor with us lived 600 million years ago and had minimal nervous system. Octopuses have 9 brains, 1 central and 8 in their arms. Their arms can make decisions independently, solving problems without central coordination. Their consciousness, if they have it, must feel radically different from ours. They're also colorblind yet change color to match surroundings with incredible precision. How do they know what colors to produce if they can't see color? This puzzle baffled researchers until recent work suggested they might see with their skin, using the same photoreceptive proteins in their skin that exist in their eyes. Their entire body might be a kind of eye. This reminds us that evolution finds countless solutions to survival challenges. Intelligence evolved independently multiple times on Earth, and primates, cetaceans, corvids, parrots, octopuses, possibly others. Each represents a different architecture producing similar functional outcomes. This convergence suggests intelligence is a natural attractor, an inevitable outcome given enough time and evolutionary pressure. But what exactly is intelligence? We struggle to define it even in humans. IQ tests measure certain cognitive abilities but miss others like creativity, emotional intelligence, practical wisdom. Animals demonstrate intelligence in ways our tests don't capture. A rat can navigate complex mazes. A crow can use tools creatively. A dog can understand hundreds of words and respond to subtle social cues. Are these different types of intelligence or different expressions of the same underlying capacity? Artificial intelligence complicates matters further. Chess programs defeat world champions, but can they generalize their intelligence beyond chess? Language models generate coherent text, but do they understand what they're writing? Image classifiers recognize objects reliably, but do they see the way humans do? These systems display narrow intelligence, superhuman at specific tasks but unable to transfer skills to new domains the way humans do effortlessly. Artificial general intelligence, AGI, would match human flexibility, learning new tasks quickly, transferring knowledge between domains, reasoning abstractly. We haven't achieved this yet despite decades of effort. Neural networks have brought impressive progress, but current systems remain narrow. They excel at pattern recognition but struggle with reasoning, planning, and understanding causation. Some researchers think we're close to AGI, that scaling up current approaches with more data and computation will get us there. Others think we're missing fundamental insights, that current methods hit walls no amount of scaling can overcome. The debate parallels earlier AI disputes. After initial optimism in the 1950s and 60s, AI hit multiple winters, when progress stalled and funding dried up. Current enthusiasm might meet similar disappointment. Or we might be at an inflection point where progress accelerates dramatically. AI capabilities have grown exponentially in recent years. Systems accomplish tasks that seemed impossibly difficult just a decade ago. Extrapolating these trends suggests transformative AI within decades, perhaps within years. Such extrapolations might prove wrong, but they're not obviously absurd. Transformative AI would change everything. An AI system smarter than any human, capable of scientific research and technological development, would accelerate progress dramatically. It could help solve problems we've struggled with for decades: cancer, aging, climate change, poverty. Or it could pose existential risks if its goals diverge from human values, if it optimizes for objectives that don't account for human welfare. Aligning AI systems with human values is harder than it sounds. Human values are complex, contradictory, difficult to specify precisely. We can't even agree among ourselves what values matter most. How do we encode ethics into mathematical optimization? How do we ensure an AI system cares about human flourishing not just as instrumental goal but as terminal value? These questions aren't hypothetical future problems. They're urgent challenges we need to solve before transformative AI arrives. Solving them requires integrating insights from computer science, philosophy, psychology, neuroscience, economics, political science. It's one of the most important interdisciplinary challenges humanity faces. But AI also offers hope. Medical AI already assists diagnosis, sometimes outperforming human doctors at detecting diseases from imaging. AI protein folding predictions solve problems that stumped scientists for decades. AI might help design new materials, optimize renewable energy systems, discover new physics. The potential benefits are enormous if we navigate risks successfully. This pattern repeats throughout history. New technologies always bring both benefits and risks. Fire enabled cooking and warmth, but also destruction. Agriculture enabled civilization, but also warfare and slavery. Industry enabled prosperity, but also pollution and weapons of mass destruction. Nuclear energy offers clean power, but also devastating weapons. Every powerful technology is double-edged. The question isn't whether to develop technology. We can't stop human curiosity and innovation. The question is how to develop it wisely, how to maximize benefits while minimizing harms. This requires foresight, planning, wisdom, qualities humans haven't always demonstrated but can cultivate. Looking at technological progress across centuries reveals accelerating change. It took thousands of years to go from agriculture to writing, thousands more to printing presses, then centuries to industrial revolution, decades to digital computers, years for smartphones to become ubiquitous. The pace keeps accelerating. Changes that once took generations now happen within lifetimes. This acceleration can't continue indefinitely. There are physical limits. You can't transmit information faster than light. You can't compute with less than the Landauer limit of energy per bit. You can't pack matter denser than neutron star material without forming black holes. Eventually, we'll hit fundamental constraints. But we're nowhere near those limits yet. Current computers are laughably inefficient compared to theoretical maximums. The human brain performs roughly 10 to the 16th operations per second while consuming only 20 watts, far surpassing any artificial system per unit energy. Biology found solutions through evolution that engineering is only beginning to appreciate. Neuromorphic computing attempts to mimic brain architecture, using spiking neurons and plastic synapses rather than traditional digital logic. These systems are more energy efficient for certain tasks, particularly pattern recognition. They might enable AI systems that match biological efficiency, running on battery power rather than data centers. Quantum computing offers different advantages, solving certain problems exponentially faster than classical computers. Factoring large numbers, simulating quantum systems, optimization problems, all become tractable with quantum computers. But building stable quantum computers is fiendishly difficult. Quantum states are fragile, easily disrupted by environmental noise. Maintaining coherence long enough for useful computation requires exotic cooling and isolation. Still, progress continues. Companies and research labs have built quantum computers with hundreds of qubits. They're not yet large enough to solve problems beyond classical computers' reach, but that threshold approaches. Within decades, quantum computers might revolutionize chemistry, materials science, cryptography, optimization. These technological developments will reshape society in ways we can barely imagine. Every previous technological revolution has done so. Agriculture created settled civilizations, enabling specialization, writing, mathematics, eventually science. Industry urbanized populations, created middle classes, enabled mass education. Digital technology connected the globe, democratized information access, created new forms of communication and commerce. What will AI, quantum computing, biotechnology, nanotechnology enable? We can speculate but will likely be surprised. The future rarely unfolds as predicted. We're bad at forecasting because we think linearly while change happens exponentially and unpredictably. We imagine tomorrow as today with minor modifications rather than fundamentally transformed. Yet some patterns seem likely. Information technology will continue integrating into daily life, becoming more ambient, invisible, embedded in objects and environments. Augmented reality will overlay digital information on physical world. Brain-computer interfaces might enable direct neural communication with machines and each other. Genetic engineering might eliminate diseases, extend lifespans, enhance capabilities. These possibilities raise profound ethical questions. Should we enhance human capabilities beyond normal ranges? Should we edit embryos to prevent genetic diseases? Should we extend lifespans indefinitely if possible? Different people, cultures, religions will answer differently. Navigating these disagreements without conflict requires wisdom and tolerance. The alternative to thoughtful navigation is catastrophe. Technologies powerful enough to transform civilization are powerful enough to destroy it. Nuclear weapons demonstrated this. A nuclear war would devastate human civilization, possibly causing extinction through nuclear winter. We've avoided that outcome for 80 years through deterrence, arms control, luck. How long can our luck hold? Biotechnology poses similar risks. Engineered pandemics could be worse than anything natural evolution produces. Malicious actors or accidents could release pathogens that spread globally before countermeasures deploy. Governing dual-use biotechnology, research with both beneficial and harmful applications, requires international cooperation and oversight without stifling beneficial research. Climate change represents another existential challenge. We're conducting an unprecedented experiment with Earth's atmosphere, raising CO2 levels faster than any time except during mass extinctions. The consequences include rising temperatures, melting ice caps, rising seas, extreme weather, ecosystem disruptions. We know what's happening and broadly how to address it. The challenge is political will and coordination. These global challenges require global solutions. No nation can address them alone. Climate change, pandemics, AI safety, nuclear proliferation, all demand international cooperation at unprecedented scales. Yet cooperation remains difficult. Nations prioritize short-term interests over long-term collective welfare. Tragedy of the commons plays out globally. But humans can cooperate when necessary. We've done it before. The Montreal Protocol successfully addressed ozone depletion. International collaboration eradicated smallpox. The International Space Station demonstrates what's possible when nations work together toward shared goals. We have templates for global cooperation. We need to scale them up. The cosmic perspective helps. Seen from space, national borders disappear. Political divisions seem arbitrary. We're one species on one planet, sharing common origins and common fate. Whatever our differences, we have more in common than we have in conflict. We're all human, all earthlings, all made of star stuff. This shared identity doesn't erase legitimate disagreements or competing interests. But it provides context. It reminds us that long-term survival depends on cooperation, that our descendants will judge us by whether we rose to civilization-level challenges or succumbed to short-sighted tribalism. Future generations might look back at our era as crucial transition point, when humanity either matured into sustainable global civilization or failed to coordinate, leading to collapse. We're living through history in the making, though we can't see clearly what story we're writing. Only in retrospect will the pattern emerge. But we're not helpless passengers. We're active agents shaping the future through our choices. Every decision, individual and collective, pushes probability slightly toward better or worse outcomes. You matter. Your choices matter. Not individually perhaps, but collectively, as part of humanity's aggregate behavior. This is both burden and opportunity. Burden because responsibility weighs heavy. Opportunity because the future remains open, not yet determined. We can still choose which path to take. We can still build the future we want rather than accept whatever comes. What future do we want? Most people, asked, express similar values: health, prosperity, freedom, connection, meaning, beauty. We disagree on implementation, on priorities, on trade-offs. But fundamental human needs and values show remarkable consistency across cultures and time. A good future would meet these needs for everyone. Enough material prosperity that nobody starves or lacks basic necessities. Enough freedom that people can pursue their own visions of good life. Enough security that violence and war become obsolete. Enough purpose that lives feel meaningful. Enough beauty and wonder that existence brings joy. This isn't utopian fantasy. Material conditions have improved dramatically over recent centuries. Fewer people live in extreme poverty. Child mortality has plummeted. Literacy has soared. Life expectancy has doubled. These improvements came from science, technology, institutions, values. They show progress is possible. Problems remain, many severe. Inequality persists. Conflicts continue. Suffering hasn't been eliminated. But the direction of travel over centuries is unambiguously positive. We're becoming more prosperous, healthy, educated, connected. We're expanding moral circles to include previously excluded groups. Slavery was normal, now it's abominated. Democracy was rare, now it's common. Women's rights, LGBT rights, animal welfare, all show expanding moral concern. This moral progress isn't automatic or irreversible. It requires work, vigilance, commitment to values that transcend narrow self-interest. But it demonstrates that improvement is possible, that we're not doomed to perpetual barbarism, that civilization can advance morally as well as materially. Your sleep deepens, brain waves slowing further, consciousness receding, leaving only the autonomous processes maintaining your body. Your heart beats steadily, 70 times per minute, pumping blood through kilometers of vessels. Your lungs expand and contract, exchanging oxygen and carbon dioxide. Your immune system patrols for pathogens. Your digestive system processes your last meal. All this happens without conscious direction, managed by ancient brain structures you share with reptiles. Meanwhile, Earth rotates, carrying you eastward at hundreds of meters per second. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at 200 kilometers per second. The galaxy moves through the local group. The local group falls toward the Virgo cluster. All this motion you never feel because you move with your reference frame. The universe continues its expansion, galaxies receding from each other, space itself stretching. In the time since you began reading, space has expanded enough that distant galaxies are now millions of kilometers further away. You'll never notice because the expansion is so gradual, so smooth, affecting only the largest scales where galaxies aren't gravitationally bound. In your immediate environment, atoms vibrate with thermal energy. Air molecules bounce off your skin thousands of times per second. Photons from ambient light strike your closed eyelids. Background radiation, mostly from the Big Bang, passes through your body constantly. You're embedded in constant flux yet experience stability through pattern persistence. Tomorrow you'll wake, consciousness returning, memories reforming, sense of self re-establishing. You'll continue your life, making choices, pursuing goals, interacting with others, all the ordinary extraordinary activities that constitute human existence. And the universe will continue too, vast and ancient and indifferent yet containing you, enabling you, being partially known through you.